Thank you. Good morning. Welcome, everybody, both in the classroom and out online. Welcome to our Commercial Energy Code class. I don't know how many have realized that this code, adoption of this code just passed the legislature 8 days ago. I was getting a little nervous that they weren't going to get to it, and all the architects and engineers that are designing to the 21 codes were going to be struggling, as would we all. How many are any design professionals in the room? Builders? Inspectors? Okay, mostly builders and inspectors, and you're with OED, Office of Energy Development.
Exactly.
Right, Chris?
Yes.
Okay. Well, welcome everybody and welcome to those online. I don't know how many of you, hopefully you have some familiarity with the Commercial Energy Code, but if not, that's okay. What we're going to do today is really just kind of touch the surface as we move through the class today. The focus is on the updates, so what changed between 2018 and 2021. But I'm going to have to put those in context with what's in the code. So we have, I don't know how many slides, 150 slides. We're probably going to run out of time on the lighting at the end, but I put enough detail there that you could follow through if you want to do a little study. I need to, of course, recognize Dominion Energy, Watt Smart, and the Office of Energy Development that makes this all possible. Most of you know I've been doing this in one form or another, for about 12, 13 years, teaching energy code classes. And it is through funding that funnels through the Office of Energy Development, and a majority of that comes from Watt Smart, Rocky Mountain Power, and Dominion Energy Thermwise. With that, my role is to teach classes. I write some blogs, some discussions on various pieces of the code. We do some podcasts. But then I think a key part where I hear from some of you is that I'm available as a resource if you have a question to reach out to me, and I can help you with those questions. If you've tried to do that recently, the last year or two, my availability has dropped down a little bit. And that's in part due to the other responsibilities I have under the contract, and then also that I'm at an age that I don't want to work all day, every single day. By way of background, real quick, I started in HVAC in 1972 and worked. So yeah, that's 51 years. So I worked at HVAC for 33 years, then as a code official for 13 years, and I retired from Salt Lake County in 2018. And so since then, I do this, and I do a little bit of expert witness work. Bottom line is, if you have questions, something I can help you with, in fact, I'm going to say this right now. We are going to be briefly going over all the provisions in the code. They apply to great big buildings. They apply to small buildings. What's going to happen is you're going to go out in July, Chris, for instance, and you have a plan come in, and it's probably like a dentist's office or something like that. It's a 1 or 2 story building, maybe 5 or 10,000 feet. That's going to be a lot different than a 17-story building or apartment project or something like that. And what I'm hoping we can do in the coming year is spend a little bit more time one-on-one with you guys in your offices and stuff. You have a building come in, and we sit down and we walk through how we would review the energy code and how we inspect the energy code for that particular building. So that's what I'm hoping we can do in the coming year. This class, even if you understood everything that was going on, you're going to sit down when a big plan comes in and you're going to go, okay, where do I start? It's just the way it works. So we are going to talk about the significant updates, the commercial provisions. By the way, if you did not know, the legislature in their infinite wisdom, did not adopt the residential energy code. So we will continue on the 2015 residential code, which includes even pieces of the 2006 residential energy code. So it's a hybrid combination of 3 or 4 different codes with, with a bunch of amendments. And if you've been to my residential classes, I have some handouts on that kind of walk you through that. Like I say, we'd need days to hit everything in detail. This is a complex code. In fact, as I've studied this with the changes and everything, I dare say, in my opinion, and maybe it's because I'm not as familiar with the IBC, that this is unequal, or even in some cases more complicated than trying to work your way through the IBC. And you guys that have worked in the IBC know how that can jump you back and forth and all over the place. Well, this one can be fairly complex, especially when you get into larger buildings. There's a lot of changes. The biggest change that took place is in previous versions of the Commercial Energy Code, you met all the requirements and then you needed to pick an additional energy efficiency item that you had to meet. And you could pick something, more efficient HVAC, more efficient lighting, and things like that. The 21 code gives you a list of things, and there's actually 11 or 12 options, and you need to get a total of 10 points. So we're going to go through that. So it makes it a lot more difficult. I ran a sample comm check on a job I worked on several years ago, and I updated it to the 21 code, could not even come close to passing, could not get enough points to pass. I increased the efficiency of the envelope to where it passed the 18 code by 45%. And I still cannot get it to pass. And we'll go through why when we get up there. But it's a big change, but it gives a lot of flexibility. So we'll review that. I dare say, and anybody wants to chime in and express an opinion, that overall energy code is the least enforced code across the state. And the commercial code is better in some cases. Simply, the compliance is better simply because when you get a large building, you have a real professional set of design professionals that know the code and design it, and they really, take the guesswork out of it because they know what they're doing. It's not. I see so many people that still call me and say, "Hey, I got a comm check here. You want to look at it?" And they send me the comm check, and it's an envelope comm check. And I said, "Well, what about the mechanical and the lighting?" "Oh, well, they didn't submit that." Well, you have to do the envelope, you have to do the mechanical, and you have to do the lighting inside and out for a complete energy compliance certificate. Comm check is not mandatory. However, it is by far the simplest method to show compliance with the Commercial Energy Code for both IECC and ASHRAE, with the exception of performance compliance options where you model the building. But any of the other options, I don't know how you do it without comm check. Why do we care about the IECC? I like to say the biggest reason is it's comfortable and it's cost effective. That's why it's important. And to bring that point down, well, let me look at the bottom. What will energy cost in 20 years or 30 years? I remember gas at 27 cents a gallon and lower. Energy costs are not going down. They're never going to go down, and they're just going to keep going up. So my oldest boy, he works for Cushman Wakefield, which is a global property management company, and his director of engineering over the western states. And so I called him the other day and I said, "Hey, Jeremiah, can you send me an example of what the utility bills are on one of the buildings, one of your properties, just so that we can drive home, what it costs?" And so he sent me this building. This is a building in downtown Salt Lake. This is a very high efficiency building, and they are using Energy Star for existing buildings where they monitor each month everything that they're doing in the building to maintain the energy efficiency. And with that, you can see over in that column over there, the Energy Star score for each of those months. I got another slide that we'll move into. This is a high-performing building, very high-performing building. An average building would have a score of 50. So this is a building that there's not a lot more you could do to improve the performance of the building beyond rebuilding it with even tighter and more insulation and such. And you can see, well, it's not all glass. So they've done some things so they could insulate and everything else. It's about 250,000 square feet. I think this tenant has moved out. They were bought out by someone. But this Energy Star program identifies underperforming buildings and targets improvements. It gives you best practices for maintaining your building, investment priorities, where do you need to spend the money to fix things. They have a building in their portfolio that they're selling, and maybe it's one they just bought. But anyway, one of their clients bought, and it has a $6 million budget to replace 2 chillers in it right now. And so this helps you keep your eye on those things and what expenses are going to be coming up. Verify savings. If you do an improvement, it verifies that if it worked. You can report performance. And if you get a score of 75, you are recognized as an Energy Star building. Of course, at 97, I think they're there. And you can also look at gas, water, electricity, waste management. We're just going to look at electricity. And of course, it helps you with your management of the building. This is from, I need to stay here, so I'll look at my screen here. First, the top is the last part, well, the 3 quarters of 2020, which is right when COVID started, and then we go into 2021 is the lower part. What did the electricity cost for a year for that building? $300,000. This is a great building. He says many buildings, those that have a score down in the 45s, 50s, are double that. Is there a reason that we should build more efficient buildings with good mechanical systems, good lighting systems, and all that? It's huge. That's a lot of money, isn't it? And if you can make an impact on that, that's a big deal. And we have a lot of stuff. We have the technologies here now. LED lighting has just changed so much. Previously he worked out at Cottonwood Properties out there, kind of by the mouth of Big Cottonwood Canyon, and they went through and changed all their lighting in the complex from metal halide to LED. And the power company came out immediately and said, your meter's broke, we've got to look at it, because guess how far their power went down? It dropped 80%. So there are things that we can do on a building, and we think, oh, that's going to cost us a little extra money, but it can really make a huge difference. So changes. I try to highlight in blue the changes, and in chapter 1 and in chapter 2, we're just going to go through these fairly quick. But so here's kind of the scope, the construction documents, and the changes are digital format can be used. The code before did not say you can, that digital was okay. Well, I think most of you are going digital right now. I can't imagine anybody wants to turn in rolls and rolls of paper plans anymore, but it's in the code now, and the information required, and the top of the list is one that I've pushed for forever, energy compliance path. It is so challenging when you do a plan review to get a set of plans and you try to figure out, so how are they complying with the energy code? This goes for residential and commercial. Which pathway are you using? And it's put it right at the top of the list that we need an energy compliance path. I've maintained on commercial buildings and you can tell your architect and engineer friends this. They've heard it because I've mentioned it in almost every class I do. You get a set of plans for a commercial building, you're going to have your civil pages, you're going to have your structural pages, you're going to have your building pages, you're going to have your mechanical pages, your plumbing pages, your electrical pages, your technology pages. How about let's put in the set of plans some energy pages where we identify exactly what the insulation is going to be in the wall, what's going to be on the roof, what the windows are going to be, rather than it's scattered amongst pages in the plans, your specifications, which 95% of the time don't match, right? I've been through that so many times because that spec book is what? Boilerplate. And so that's what happens. How do you build a building if your documents are not great documents? There are jobs, and some of you have heard me say this before because it will haunt me forever. There are jobs that I wish when I got the plans and I looked at them and I realized they were garbage, that I wrote the builder or the developer a check for $5,000 and said, here, go get someone else to do it, because it cost me way more than that to do that job that just went to hell because the plans were so horrible. So you're laughing back there.
I was a general contractor for 10 years. I worked for like 50 years.
Yeah.
Yes.
She knows. You literally can lose a lot of money. And you as general contractors, you know if the architect gives you a crappy plan and you're always looking for more information and more information, you're just wasting your time. So a good set of plans with a good review makes the project move smoothly. And that's why it's so important. Down at the bottom, we have air barrier, air sealing details, including the locations of where your air barrier is. My air barrier is on the outside, it's on the inside. Yeah, but it stops here and it starts again here. We have to have a complete air barrier. And that's stuff that should be on the plans. Compliance pass. The commercial is really fairly simple. You have your administrative section in the code, the definitions, you have your climate zones, your general requirements, then you go down to energy efficiency, and you have new buildings and you have existing buildings. Existing buildings are in Chapter 5. And then you have to make a decision. Is it ASHRAE 90.1 or is it IECC? We are not going to go into ASHRAE right now because that would be another huge conversation. But I will say this, IECC with the changes that we're going to talk about today very closely parallels ASHRAE now. They're very, very similar. So you're going to see the same stuff. And then from there it says we can either go prescriptively or we can go performance. Now just real quick, prescriptive is the table and ComCheck and such, and I'll go into that in the next slide or two. And then performance is a model. They do a model of your building. They put in everything that's going in the building. They compare it to a standard reference design building. And if you pass, you're going to use less energy, and they want you to pass by 15%. Then you comply with the code. If someone wants to do performance, they still have to put on the plans the thermal performance specifications. So with IECC or ASHRAE, you have to pick one. You can't pick and choose. It used to be you could use ASHRAE for the envelope and you could use IECC for mechanical and lighting, and sometimes they did that because ASHRAE was a little easier on vestibules. You can't do that. You pick one. The prescriptive path includes you either follow all the tables exactly or you do a trade-off with ComCheck on your envelope. Commissioning depends on the size of the building. Notice that's on the bottom. You don't have to commission every building, but if it uses a lot of energy in heating and cooling, you will have to commission it. This is what the last code, I had this diagram put together. Actually, DOE put this together, and they haven't put out a new one. But we'll just talk real quick. So you pick ASHRAE or IECC. In the 2018, if you picked the prescriptive table, you went down through, you had to pass on the envelope, you pass on the mechanical, pass on your service water heating, pass on your lighting. And then you had to pick what of those, what was there, 8 different things, and you just picked one. And for instance, there's high-performance HVAC, reduced lighting power, on-site supply of renewable energy, dedicated outdoor air systems, high-efficiency service water heating. Now let's just pick that one for example, high-efficiency service water heating. If you're building a building and it's a warehouse with a little office and it has 1 bathroom, you cannot use service water heating because how much hot water are you going to use? Nothing, right? Enough to wash your hands. That was limited to high water usage, hotels, schools with locker rooms and stuff like that, apartments, and we're going to talk about that in the new code. What changed is we don't have that list of 8, we have more items, and we can pick multiples, and we get points for each one of those. And then on the other side is the performance, where you do a model. You don't do it, the engineers do a model. Res check, COM check. How many are familiar with COM check? Few? Guess what? You cannot download the 2021 COM check. It has to be done online. Only COM check web is available. So good luck to you. It's got a learning curve. I've been messing with it for the last week or 2, and there's some challenges with it to me. But anyway, for compliance with the code, you see the orange boxes. You have to have a compliance certificate for the envelope. You have to have one for interior lighting, one for exterior lighting, one for the mechanical. And then you see next to that, the box for credits. That's where you decide what efficiency packages you're going to use. So, Chris,
So I get some of these
hang on.
I see some reports come in, and I can't identify that these are all standalone or a single report as far as the envelope, mechanical, lighting. How can I identify, or is it necessary that they be one combined report?
So you're asking that they're all the same building, or they're?
Are they done independently? Can they be, or do they need to be coordinated?
Well, in the last code, when we were back here, when you had to pick one of these, when you pick one of those, it has to reflect that on all 3 of them, because each one of them has a line for that. Each one of them has a line that says what's your additional efficiency selection. And there was a lot of arguing and stuff like that because, well, I picked, that someone picked lighting and everybody else picked, something else. And they have to be the same. This one is actually going to get, in fact, I got a slide in here. The design team is going to have to play nice, and they're going to have to work together because they can't be done independently. One guy can't do one, another guy do the other. They're going to have to all be done the same project, and I think maybe that's one of the reasons it's gone to web, because you're going to be getting points from lighting, you're going to get points from mechanical, you're going to get points on your envelope. And you might have 3 or 4 options that you get a few points on as you move through. Does that make sense? It's a different world, but it actually is going to bring that design team together like they should have, and they're not each trying to do something, their way and not care what happens to the other guy. Good question. So anyway, I downloaded it 3 times before I read the note that said it's not going to be in it, so what you download. But that was my error. We have some definitions, and we're just going to kind of fly through them. And the reason I'm going through these definitions is because they tie into that additional efficiency area that you're going to grab some points. And some of them are tied in with renewable resources and such. And so we have a definition now for what biogas is. And it's basically gas between, hydrocarbon gas between 60 and, that is a gas at 60 degrees Fahrenheit at 1 atmosphere. And it comes about by decaying organic matter. Biomass is similar, but it's just not gas. It's, it can be gas, but it's all these things, and I'm not going to read through it. But again, it's non-fossilized biodegradable organic fractions of industrial municipal waste, including gases, liquids recovered from the decomposition of non-fossilized biodegradable organic material. So it's pretty clear. On-site renewable energy, and this is one of the areas that you can get a lot of points, and it's kind of simplified. The gray crossed off is what was taken out of the code, and the new definition is energy from renewable energy resources harvested at the building project site. Why do we saying at the building project site? Because people are putting PV panels someplace else, getting credit when they do their lead building. There's a bunch of panels they paid for on a warehouse roof, and they're getting credit for their building that's in downtown Salt Lake because that's putting power into the grid and they get some credit for it. The code is looking for on the site renewable energy resources. We have them all there. I don't need to spend any more time on it. Climate zones. Our climate zones changed. In Utah, the changes that took place here is Box Elder, Cache, and Carbon County moved from Climate Zone 6 to Climate Zone 5 because they're not as cold as they were. Historical data on them shows that they're a little bit warmer. And if you look at the map closely, you can see that Box Elder is the upper left, if you don't remember, and Cache right next to it. Then Carbon County's down there, Price. So those are a little bit warmer, and so they've moved from 6 to 5. Does this look familiar? On the residential side, we were supposed to put a label someplace that identified the envelope, a certificate that identified what's in the envelope, which would be nice for your HVAC guy when he comes back in 20 years and wants to change out the system, wants to do a load, and he wants to know what's in the walls and such. So it's R values and U factors and any results from leakage testing that took place on the building. Greenhouses, I bet I've had 8 or 10 calls on this. Does a greenhouse have to comply with the energy code? And what the code's really calling it is one of those that's exempt if it is strictly for growing. That's the production. It's really production energy. It's not building thermal energy. And there are a few requirements for that. If down at the bottom, they're exempt from the rest of the code, the building envelope requirements. They are not exempt from lighting requirements, by the way. They're exempt from the building envelope requirements, except down at the bottom, fenestration assemblies have to comply with the table. Skylights at 0.5, vertical fenestration at 0.7. That's pretty, easy to meet. If they have an opaque roof assembly, then there has to be a little bit of insulation in it. Cell tower type buildings, these little equipment buildings, we have identified in the code that if it's less than 1,200 feet, you and it uses so much power, you have limited insulation required. Basically, climate zones 1 through 5, you only have to have R5 in the walls and roof, and if it's a colder climate, you only have to have an R8 in those, and the rest you're okay on. Has to have a compliant roof. If you're in climate zone 3, it has to be reflective roof. Building envelope requirements. This is addressing what do you do if you have too much glass. We see buildings all the time that are all glass, right? And you say, how can you be that? How can you do that? Because energy code says you're going to be 30% glass. But then energy code goes on to say, and I have a note there on it, 30 or 40%. You can have 40% glass if you're doing what? If you're using daylight to reduce your lighting load. So you can increase the amount of glass if you're using that daylight as part of your energy savings. This building right here, we have windows right there. We have a daylight zone that comes in so far into the building, and according to the code now, we're supposed to, and it's been in the code for 6 to 9 years, we're supposed to be able to shut down lights as you step into the building, because you don't need lights on if they're receiving light from the windows. We see it in big box stores and Walmarts and stuff like that. You walk in and you might see, seems like the lights just dimmed down. Well, they did because there was enough coming through the skylights that automatically shut off some lights, so you didn't need them. So you are allowed to have more glass if you do that, but if you have more than 40%, then you're going to have to go to the performance model, or you're going to have to go to ASHRAE and do a performance model there to have that amount of glass. And then we have some new requirements for walk-in coolers, walk-in freezers, and all those things. In fact, I might even got a call from you, Chris, once about used walk-in boxes or something. And that's one you're going to have to deal with on a case-by-case basis, because there's efficiency requirements for all that refrigeration in restaurants and such now, and storage and refrigerated warehouses. So the prescriptive approach, we have a table, and I know you can't read it. If you open your code, you would see it, but we have prescriptive table. And if you want to go prescriptive table, you simply meet everything in this table, and you comply with the thermal requirements of the envelope. You still have to air seal and stuff like that, but you just follow prescriptive table. And so let's look at what's happened here. For roofs, in climate zone 6, in climate zone 6, we'll notice where they've crossed out, and this is for a metal building, that it went from R25, R11, and a liner system. Anybody familiar with liner systems for metal buildings? You will be in a minute. So the insulation they're talking about, R25, and well, it's changed to R30, R11, and a liner system. So what they're saying is you blanket R11 across all the purlins one way, then you put 30 between, but then the LS, the liner system, means you have a vapor barrier that goes underneath everything. Because what happens with a metal building when you heat it? They condensate like crazy. They drip everywhere. We have a requirement in there too, in the walls for thermal blocks and stuff like that on your purlins to give us a thermal break there. But for a number of years, metal buildings were kind of given a pass. They weren't required to be as efficient, but that's gone now. They can be energy pigs, and so they need to be more efficient. Walls above grade. If we look at that, we can see crossed off, and you can see this on your full-size slides, but you'll notice in 5 and 6, our two most common climate zones in Utah, every one of them have an increase in our requirements there. Improved R values. for heated slabs, and I don't know if I have a slide in here, for heated slabs in a commercial building, you have to put some insulation underneath the entire slab. You have an increased amount required around the perimeter, but you have to have full insulation under the whole slab. Walls above grade, below grade, that's gone from 7.5 to 10. Floors, again, that's increased. And if you have a question, just stop me. There we go, slab on grade floors. And the insulation requirement has gone up on those. And opaque doors. You know how garage doors and such, non-swinging doors, have always had an R value assigned to them? So you have a metal door that has all this metal thermal bridging, and the code's been saying, well, put R4.5 or whatever in the panels. Well, is that representative of how that door performs? Not at all, because we have that big thermal bridge every time that metal wraps around. And so the code has finally said, the manufacturers are going to need to have them tested and assign a U factor to them that takes into account the thermal bridging in that, what they're calling non-swinging door. Yeah, they're going to be whining. So I thought I'd throw this in because metal buildings are kind of confusing sometimes. As I was describing, notice I have thermal blocks on top of the purlins. They're rigid foam. They're oftentimes encapsulated so that we don't lose shear, so we can fasten through it and it's rigid and we maintain shear. But you drape and then add insulation parallel. So we have insulation draped and insulation that's parallel. And there's our requirements over there. Then the liner system down here. Continuous vapor barrier liner membrane that is installed below the purlins and uninterrupted by framing members. Uncompressed, unfaced insulation resting on top of the liner membrane, located between the purlins. Moldy layers, the last rated R value is for unfaced, draped over the purlins. And so that's what those systems will look like. And there's a vapor barrier that's over everything. You might see some little strips that they put on there to help support it. And you might encounter them. In fact, I've seen some that you can see the structural beams, that go up and over, but the liner has to go over the top of them. So the liner goes down first, then they insulate, then they put the deck on. Go online if you need more details on it. But that makes for a good system. Minimum skylight areas. If you build a building greater than 2,500 square feet, floor area directly under a roof, with 75% of the ceiling height at least 15 feet or higher, you have to put skylights in it. Now you can go to your code official and say, no, do I really have to do that, and justify why you don't. But generally you have to put them in, and the VT on the lights should not be less than 0.4. What's that trying to say? We run into where we need a balance point. If windows are great for lighting, what are they not so great for? Thermal performance, right? A great window is going to be someplace around R3, a triple pane window will be R5. That's not very good, is it? So we want to grab the light, but we don't want to give up all the thermal performance. And so we have limits. We can increase it a little bit, as we'll see on another slide. But when we put solar heat gain coatings and such on windows, sometimes we block the VT, the visible light. And so we have this thing in the code where we're trying to balance. We need enough VT to let the light in. We want to reflect the heat out in the summertime, and we don't want to have too much heat loss through the glass. And so there's not one perfect answer. Too often, we think, oh, this is going to solve it. You know, you want to put a heat pump in. It's going to solve everything. No, it's not. It's a piece of maybe an energy efficiency plan, but it isn't the total answer. I've seen this year after year after year for 5 decades now. Something comes out. Back in the 70s, we had a big push for heat pumps, and they weren't that well performing. And that's one of the challenges now, is there was a lot of bad experiences with heat pumps back then. And then the power company tried again, and we've gone through these different cycles, and a heat pump still is not perfect in all cases. And so we need to understand that we have to make wise decisions depending on what building, how our building's built, and what we're doing with the building. So the code used to have all the windows and doors in separate tables. They've tried to consolidate them in one, but we now have some limits on how much glazing we put in our door, and we need to have a U factor. That's the big thing that's new. For these overhead doors, it was an R value that we had to be assigned. These metal doors, these heavy industrial, commercial type man doors, they need to have a U factor on them. You know, we can't ignore them. Air leakage. Our good friend Bill Vanderlinden, that passed away, I don't know how many years ago, when I got into code, you know, on the inspector side, we used to argue about air sealing. And he liked to say, Brent, why don't we just let the building leak so we don't have the indoor air quality problems? And why don't we just let them leak and not have to worry about all this ventilation stuff? Anyone dare throw in a comment? I'll tell you why, since no one's brave enough to say anything. What we're relying on in that case is infiltration. What's the definition of infiltration? The uncontrolled leakage of air in and out of your building. So what happens when it's uncontrolled and the wind blows? Your leakage rate goes way up. In fact, I experienced as a contractor up at the mouth of Parley's Canyon, every so often we get a really cold spell and the wind's just coming down the canyons. And if you have a leaky house, I don't care if you have a 300,000 B2 furnace, it's just pushing the air all the way through the house because it's leaking. And so reducing air leakage is a big factor. It also helps us maintain air quality. We can filter it better, and we can control indoor air quality better. If we are exhausting at the source, we exhaust, you know, from our bathrooms, we exhaust the places we create water. Where if we're trying to rely on infiltration just moving through, what we're really doing is changing the air, for the most part, just around the perimeter of the building, inside the perimeter, and not getting the fresh air where we need it. So anyway, for air barriers, what's changed in the 21 code is basically dwellings all need to be blower door tested. And there's a lot more building thermal envelope blower door testing. So we're seeing a large increase in testing of the envelope, and then we have a change on operable openings. And what I'm talking about are like for restaurants or something like that. You have a big window door assembly that opens up. When it's mild, they might have some patio heaters out there. We have some requirements that require some interlocking of the HVAC when you open those doors, so that we're not trying to cool outside or we're not trying to heat outside. And we'll have some slides there. So our air barrier, our testing, for all your R occupancies, you need to meet that section 402.5.2, which is dwelling and sleeping unit enclosure testing. And you have to test at 50 pascals. What's that? That's the test that we've been doing on residential forever, right? Exception is 2B, 3C, and 5C. Does that impact Utah? No. We have 3B in Washington County, but that's it. Other than Group R and I occupancies, you meet the next section in the code, and that's test to 75 pascals. So you're stepping up the pressure a little bit. You can leak a little bit more because you're using an elevated pressure. And 3B does fit into that one as an exception. And then buildings between 5,000 and 50,000 feet in climate zone 5B also fits in that exception. And I haven't quite figured out, I've read the commentary and stuff. I need to pull the code change when what was submitted to identify really why they did that. But there are some exceptions to this. And then those areas that don't need to test have to verify that there are air barriers in place, and it requires verification. The building official can do that, but the building official can require third-party verification of the air barrier. Now that's 6 blower doors. You get a larger building, you're going to need more than that to pressurize the building. And in fact, really large buildings, they can actually, with a guy that knows the building management system, they could pressurize the building with the HVAC unit and take it to 75 pascals and be able to identify that. I'm not going to obviously read through all this, the testing, they're just defining. This is the first one, the sleeping units. You can leak 0.3 CFM per square foot at 0.2 inches of water gauge, which is 50 pascals. But it does give us some direction, and I've received a lot of calls on this. Down there at the bottom, if you have fewer than 8 units, you have to test them all. If you have 8 or more units, the greater of 7 units or 20% of the testing units in the building need to be tested. So if you have 300 units, you're going to have to test 20% of them. For each test unit that exceeds maximum leakage rates, so each unit that fails, you need to test an additional 2 units. And then it gives us some direction on which units, you have to pick a top floor unit, you have to pick a bottom floor unit, you have to pick one of the biggest units and do that testing. So you don't have to test every single one of them, but you have to follow that there. For the next one, where you, other than those R's and I's, kind of similar things, you test the entire envelope of all stories that have space directly under a roof. So you have a larger building, you have to test the whole to upper level. You have to test all levels with the building entrance, exposed floor, or loading dock, or our below grade, and then representative above grade building sections of at least 25%. So, and then there's some exceptions to that, but it gives us a little bit of direction on that. And then if you fall into those groups that you don't have to blower door test, then you have to verify your envelope. And that's either an engineer or a code official or another approved, a third-party agency, review the documents. It's like a special inspection for your air barrier. And other supporting data, inspect continuous air barrier components as it's going together, and provide a final commissioning report that person is, certifying that all those components were used and they observed them being put together. And here's our operable openings. You have a restaurant. If the door is greater than 40 square feet, that's not a very, very big door, is it? And if you're leaving it open, they must be interlocked with the heating and cooling system. What it does is it raises the cooling set point to 90, and it lowers the heating set point to 55 for that space just inside. And there's exceptions for food prep areas, warehouses with overhead doors. That's a function of their occupancy. And vestibule doors. Any questions on that? I've heard lots and lots of calls on that, and that's kind of what we've kind of decided is the best way, is we disable that unit that's right in there, because we all know that you've seen them open and the HVAC system's just running wild. That's what my grandkids think you're supposed to do, is leave the doors open and see if you can cool outside. So our credits. And this one is where we get into what I talked about just a little earlier. So yes, we have a number of tables in here, and we get credits for better HVAC, reduced lighting power, enhanced lighting controls, on-site supply of renewable energy. Remember we talked about renewable energy at the first? Provisions for dedicated outdoor air systems for certain HVAC equipment, high-efficiency service water heating, enhanced envelope performance. So what would that be? Insulation beyond what the code minimums are. Reduced air infiltration, make it even tighter. Energy monitoring systems, if that's not already required. Sometimes they're already required. You cannot get credit for something that's already required because of the type of building you're building. You don't get extra credit. You can't double dip it. If it's not required, include fault detection and diagnostic systems on your HVAC. When you hit a certain size on a building, you have to have fault detection and diagnostics on your HVAC. But if it's a smaller building, you don't have to. And efficient kitchen equipment. There's a lot of new things here. Now, what's really not mentioned here, well, it is in a way because, and you as code officials need to be aware of this. All of our buildings, all of our new high-efficiency commercial buildings that are being built now, almost all of them include an evaporative cooling component to their cooling systems. And they save a huge amount of money. I'm sure some of these larger buildings that have been built around here, in that big air handler, whether it's a manufactured air handler or a big penthouse built air handler, there will be an indirect and a direct evap cooling section in that unit that's ran by the building management controls, and you're never going to be aware of it because it's not like your standard swamp cooler you have on your house. If conditions are dry, you can cool a big building without ever turning the chillers on. My son has mentioned many, many times, lots of times, he doesn't start his chillers. Well, he starts them to, they start them to check them, but the chillers don't even start running until into July sometimes. And the energy savings is just huge on those buildings that you do that. And so with this, the design team can justify it, might need to provide some calculations to show the energy savings. Prior to this code cycle, you didn't have a way, but more efficient HVAC performance, it's easy to document, easy to show that you can do that. And that really, used wisely, could push any building that includes that over that 10 points because it's such a big savings. I got an example in here we'll talk about in a second of that. That's massive amount of savings. So here's what it looks like. And this is hard for me to, my screen's too little here and I'm on an angle here, so. If you notice this table, it says table 406-1, parenthetical 1, additional energy efficiency credits for group B occupants. So this is a group B building. It's office building. And here's a list on the left-hand column of all those things that you can get credit for and what you can't get credit for. If you go down 3, it says 10% heating. So you improve your heating efficiency by 10%. For those that are in here, it's right here. 10% heating. And then you go over from it, it says NA, 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 all the way across until you get 4A and through, and then again, and then when we get to 5A, 5B, 5C, we can get a couple of points. Why can't you get any points in those other climate zones? It's a warm climate. Exactly. But if you look at cooling, you can get points in those warm climates, right? You can get a lot of points for cooling. There's some good logic to this. It's a B, you know what I mean? So, and look at that. If you're 1A and you improve your cooling 10%, you get 11 points, 12 points, 10 points in those first 2 climate zones, 2 or 3 climate zones. You've done it with a B. Because
What is 10%?
10% energy efficiency.
So is that like 90% efficient, or what are we talking about? What's the efficiency?
Yeah, the total energy, total cooling energy, total heating energy, if you reduce that 10%. And it is directly related to your SEER ratings or AFUE ratings. And you can buy, more and more efficient. You can't go much higher than 96% on a gas boiler, but yeah, so you can see kind of what happens. Of course, notice down on service water heating, you don't get anything in a B, because how much water do you use in a B? How much hot water do you really use in a B? Not very much, right? In fact, these big office buildings are moving away from a water heater in a mechanical room someplace and a big circ pump, because that's horribly expensive and you're using tons of pump horsepower to push all this water around. And then you run into a piping challenge on that we'll talk about in a minute. And it's simpler to just do a nat source water heater and you make it at the source. I mean, it saves so much money all the way around. And so each one of these tables, and I'm not putting up every table, but I am going to put up some as we get further down. Now, I'm going to alert you to this, that we're finished with the envelope, the changes in the envelope. Pretty straightforward. I'm going to revisit this table 2 more times. I'm going to visit these tables when we get to the mechanical systems, because some of these are mechanical. We're really focusing right now on the envelope, but we're going to have tables that fit those mechanical areas. We're going to have a table that fits the lighting areas. And so we'll revisit this again, and we'll include a couple of the other tables. We have separate tables for Group B, multifamily R and I's, schools, retail, and then other than above. So schools and multifamily, they can get some for your service water heating because they can use a lot of water. High schools, how much water do they use with athletics and everything like that? So it makes a difference. And then someone mentioned something that maybe before we started here, tenant infill, TIs. You have to have 5 points. Now, there are some exceptions to that. But it really, really points to, if you're building a TI building, it would really be to your advantage to try to make what you are putting into the shell as efficient as possible, because if you can meet the shell, satisfy this requirement with your shell, then you don't have to worry about it as you're doing the TIs. You get to the TIs and you're trying to do your TIs, and it can be really difficult to try to get 5 points when all you're doing is finishing out an office. So a good envelope, if you're rough in mechanical that's efficient enough, and try to get the compliance when you put up the shell. And if you have that building that complies, then you don't care which code cycle they do the TIs because you already have a shell that complies. Okay, with that, I'm going to just digress a little bit because it's part of what I need to do, and I think it's good information because a lot of you guys are involved in residential. But over the last 4 years, DOE has been doing a study in Utah, and you might have heard something about this. But we did a study on residential buildings, and we do have residential in the commercial code when we get to larger apartments. But what we found on, DOE had us hired people to go out and study a bunch of projects. And it was a team that included Office of Energy Development and a bunch of other, Nexent, who is now Resource Innovation, that Jacqueline works with. And a number of people we got together, and we were the project team and kind of managed this project. And we finally, after COVID, got the results out. They studied about 126 buildings to create a baseline, and it's so we can develop education to meet our weaknesses. And these are the things we studied: envelope tightness, windows, wall insulation, ceiling insulation, lighting, foundation, insulation, and duct tightness. And that's where we'd studied homes, most of it in the populated areas. But what we found through this study is that our exterior walls are the weakest component in our single-family dwellings. Why is that? Because we have a ridiculous, I'm going to just say that how it is, we have a ridiculous amendment that says you can trade off a furnace for a crappy wall. Isn't that what it says? Those of you are familiar with the residential code. You can build a 2x4 wall, you can put R11 in it if you put in a 96% efficient furnace. And so they were looking at what the code says, not what our amended code says, and they said that if we built with code minimum walls, R19 generally, energy savings each year would be about $620 million. Duct leakage, big one. We know ducts leak. But the one that was surprising was envelope air leakage is low. Why is envelope air leakage low? Because builders, because of their stuccos and everything else, are actually building a pretty tight envelope. And when we test them, we kind of find that out. So I'm just going to jump ahead here real quick. That did not focus on HVAC systems and ventilation and stuff like that.
Brent, that's not going to be an affordable home if you do that.
If you do what? If you insulate the wall a little better? I know you're being facetious. This past year was the first year that my property tax was higher than my utility bills since I've been in my home. And it's only because my property tax went up $1,000. But every year previous, my utility bills were higher than my property tax, which meant the second greatest expense the typical person has, and then maybe it's kind of fluctuating between second or third or equal. So number one is your mortgage. Number two, utility expense. Number three, your property tax. And maybe 2 and 3 can trade off a little bit. And I know you're being facetious because we build a good wall, and every study done, every model done shows that it pays off completely in less than 5 years, but it has an immediate savings. If you add the cost of an R19 wall to your mortgage, the cost is much less than your fuel cost, your heating and cooling costs through that same period of time. So it's like I was up at the legislature testifying once before Business and Labor Committee, and I said, if we did not have an energy code, There are some builders, for you builders, I know it's not you guys because you're here. You're the ones that come to it. It's the ones that never come to it, everything. But I said there's some builders that if we let them put in single pane aluminum windows, they would. And this genius up there said, well, maybe that's all they can afford. I had to bite my tongue to say that's the most ignorant thing I've ever heard, because no one can afford single pane aluminum windows with what fuel costs are, because you'd make up the difference from a good window to that window in 1 or 2 years in energy costs, maybe less than a year. I mean, it's such a crazy statement. The U factor on a single pane aluminum frame window is like 1.25, so it's like an R.7 window. I mean, it's just crazy. But anyway, the big thing, so yeah, insulation needs to be improved. But the big thing we came up with is our air leakage is low, which, let me jump to this one. So the code, generally, the vast majority were tighter than 3.5 air changes per hour. If we did not amend the code, anything under 5 air changes per hour would require mechanical ventilation. So the vast majority of the homes we're building right now are tight, and the vast majority of the homes we have do not have mechanical ventilation. So that's my whole point, and the reason I want to bring up this study. What is mechanical ventilation? That is where we actually mechanically create those air changes. We exhaust it from where we need to exhaust. We exhaust it from the bathroom. Mechanical ventilation could be as simple as putting a Panasonic fan in the master bathroom, setting it to run continuous. And you can adjust the speed on them so that you're always exchanging some air. We have huge number of water, mold. There's so much litigation going on right now because of that. And it's because we're not, part of it is water from outside, but big part of it is condensation. We're not ventilating. I was involved in a case that they built some townhouses. They built them out of insulated concrete forms, ICFs. How much air leaks through an ICF? Basically nothing. They didn't do any mechanical ventilation, and they chased window leaks forever. And they caulked and they resealed and they reflashed windows, and it didn't do anything. Why? Because the windows weren't leaking, they were condensating, because that was the cold spot. So it's just really important. So I thought I'd share that. Okay, we'll move on to the mechanical. You know what? We just might make it. We're moving along good. But guess what? Mechanical is going to go longer. Why? Because that's someone's specialty. That's someone's passion. Maybe that means I know this better than I know the other subjects. What's that a picture of? What? A train? I put it in there. It's a mechanical system. I put it in there because it's something that the code actually recognizes this year. It's a computer room cooling system. And it's a 3 compressor, I believe. There's 3 compressors over here. They're water cooled down here. Those are the condensers. And here's the evaporator coil up here. And then you see a whole bunch of controls. So, and that unit probably was $40,000 or $50,000, maybe more. What's so important about a computer room cooling system? you need the ability to maintain humidity, temperature, and as it fluctuates all over the place. For years, and I was involved in this industry, and I put some of these units in. For years, it's kind of been, well, you got to have the computers cool, so we're not going to worry about efficiency on them. Our data centers are getting so big, there's computer rooms in just about everything nowadays, and so the code has addressed that to address the efficiency of those systems. They're wonderful jobs to get because they're pretty simple jobs and they're straightforward. But that's our introduction to mechanical equipment. So what's happened, the organization of the mechanical portions of the IECC is in these sections. We have our general, we have our system design. We're not going to talk about that at all. Those two things are our loads and our system design because we don't have any changes, but we have equipment efficiencies and specs, and that changed a lot. Every single table that you've seen in the energy code where it goes through all the different types of systems, mechanical systems, they've all changed and they've added 4 more to it. We have HVAC controls that have changed a lot. Not much on economizers. Something that we might just touch on a little bit, nothing on VAV or ventilation and exhaust. Fan efficiency. Fan horsepower. Fans can use a lot of power. Large diameter ceiling fans, heat rejection, refrigeration, construction outside the building, and operable opening interlock controls. So that last one, C403.14, we talked about that with the restaurant. There's an envelope component to that because we're putting a hole in the envelope, but there's a mechanical component because we have to shut the mechanical on and off. So it's found in the envelope section of the code and it's found in the mechanical section of the code. And so these are the things, performance, controls, guest room, HVAC. Has anybody stayed in a new hotel lately that they gave you a key so your lighting would work and your mechanical would work? Did they give you a third key and say just put it in there and leave it in there? Kind of defeats what the requirement is, but the idea is if people are not in the room, we don't need it. All the lights left on and the TV and everything left on. We need the unit shut down. And it can be done. Bigger properties are tied it into their whole building management system, and it's tied in with their reservations and everything, and they can have it start up an hour before the guest is scheduled to check in, and they can do a lot of things with that. And with those types of control systems, they can run the ventilation every day for a little while to maintain air freshness and such in that. Ventilation controls, we'll talk about energy recovery ventilation. I think most of you are familiar with those. If not, we'll touch on that. Refrigeration equipment performance, walk-in coolers, and site built-in coolers. Definitions. So we have a few definitions that tie in mechanical. And the definition ITE is kind of redundant because I see it all the time. It's ITE equipment. Well, so you're saying information technology equipment, but I'm being picky. Includes computers, data storage devices, servers, and network and communication equipment. Is this big business nowadays? We have data centers now that are just massive. Covers, block after block after block that are just huge buildings. I tried to get my other boy to send me pictures of his IT director at SpaceX, but he can't send me anything from inside SpaceX because they do government contracts. But yeah, he has big data centers all over the country at every location that are just covered multiple square blocks of. So it's big. Everything's with it. Anybody seen the Facebook data centers down in Eagle Mountain? next time you're flying in, you ought to look out that way towards Eagle Mountain, because you can't miss them. They're great big buildings. They've built 3 or 4 of them now. I have some pictures from the first one, and it's kind of mind-boggling on what they're doing for their IT. What is a data center? Has IT equipment power density exceeding 20 watts per square foot of conditioned area. Total IT equipment load greater than 10 kW. A computer room is basically smaller, less than 20 watts per square foot. And we see them in just like little closets. We see them in a room like this. This would not, if this room was full of servers, it would be a computer room. It wouldn't be a data center. It would fit in that definition. Direct digital controls, DDC. When I started in HVAC, in fact, I was going to throw a picture and I forgot to do it. About 25 years ago, a building up on South Temple, we took out all the old systems, and I scored a 5 horsepower 2-stage air compressor that was part of the HVAC system. And they had just replaced it. What was that 5 horse 2-stage compressor for? Pneumatic controls. You remember those? Remember them in schools that you'd hear a hiss from the thermostat? They're using air pressure to open dampers and do all that stuff. We've come along. Then we did what? We go to thermostat wires and we turn this on or turn that off. We now have these direct digital controls that you can't even wrap your head around everything that they do. The image I have here is one of 6 air handlers, and this I got from my son here in Salt Lake. And it's taking temperatures, it's taking pressures in the duct, it's looking at all these different things. In fact, if I can see it, right after this blower on the lower, in here are the 2 evap cooling sections. And then the third one is the chilled water. But with building management systems, from his phone or one of his engineers' phones, they can look at a building, see what's going on, they can change set points, they can detect faults, they can do all these things, and that's all part of this direct digital controls. I mean, we have all this stuff that we can do with our phones. It's amazing what we can do here, and they can look at all the lighting, they can look at, you can do just about anything you want. And it's given so much flexibility and given the ability to save energy, huge amounts of energy. But it's defined, and we don't need to read through the definition where we're going from analog or binary to back and forth, but just suffice it to say we're using computer technology to control our buildings now. And these are typically, they're not standalone on bigger buildings, they're a component of the building management system that's doing everything. Fault detection and diagnostics. These are, and I think there might be some people online that, looking at the list here, that are aware that, for instance, economizers. We have, if you went around the state and looked at all the economizers on roofs, you're going to find a large percentage of them aren't set up right, and they're not saving energy. Some of them are wasting energy. And so those they really need, as we get into these complex HVAC systems, we need to be able to detect when something's not working right. And it's a matter of sensors and stuff like that, where we collect some data and identify automatically that there's some faults. And it can prioritize and identify if it's a serious requirement or what. But that's defined, and it is a big piece of the mechanical. And it does make it more expensive, but it can surely save a lot of money. So data centers now, this is all completely new in the code, and that's why we went for definition. And we have 2 tables and a reference to ASHRAE 90.4, which is the ASHRAE standard for data centers. So if you have a project that comes into your jurisdiction, for you code officials, the first thing you're probably going to want to do is get a copy of ASHRAE 90.4 to see what the requirements, or better yet, you might need to send that one out and have someone do that review, because it's going to be a complicated review.
So I can send it to you.
No, I don't want to do it. You can send it to, there's plenty of people that can do it. But you know, I mean, I'm being a little facetious, Kurt, but I am happy to look at anything that you have, but I can't do a full review for you. That's not, you know, I don't have the time and the bandwidth in this to do that, but I can definitely give you some direction and tell you which way to go. I mentioned before, maybe before we went online, is as you go through this and as you start having plans come in the latter half of the year, we're going over some stuff that's pretty technical. And it's not the same as the convenience store that they're going to build around the corner or something like that. You're going to have small buildings. You're going to have big buildings. And hopefully we can make it work where when you have that dentist's office or a convenience store, that I could stop in and we sit down for a couple hours and we go over what we need to look for and how we would comply with the energy code. It'd be good for me, it'd be good for you, and then I could share that experience with others. Because it's important that we can get our heads wrapped around this. Like I say, they've been given a free pass for years. However, they get so big and they use so much energy. So we have 2 tables we need to refer to. Here's our diagnostics. Building engineers now that are maintaining these buildings, they just love these because, why? They don't have to drive to every building and try to figure out what's going on. They can identify which contractor they need to have come out. And the contractors, if you have a contractor that you've hired to take care of a particular building, he can be alerted. He can know when there's a problem. You can find them immediately. You know, we had the earthquake just after COVID. Downtown was pretty much shut down. I don't know how many realized, but there was a lot of minor damage to a lot of buildings downtown. And my son lives downtown, and right after, he just about got bounced out of bed because they were close to the epicenter. His phone alerted him that they had flow on the boiler. Well, guess what had happened? You know, what do we do when we go into a grid ceiling? We make them put wires on the lights, right? And all these different things. What do we make them do to the VAV boxes? Nothing, right? You know what I mean by VAV boxes, a lot of you. They're a little box hanging up there in the ceiling. They might be just a little box like this. They don't weigh enough that the code triggers seismic necessarily on it. But what hooks to them? They're on the perimeter, hot water pipes, right? Little small copper lines. So we get an earthquake and you got a 16-story building and those start swinging around because there's not a set of wires on them. What does it do? Snaps. The copper lines go into the reheat coils and you have stinky chemical treated boiler water spraying out into the ceilings in 3 or 4 spaces in your building. Now, he got the alert immediately that the BMS told him that the building boiler was requiring a lot of water all of a sudden because they have auto feeds on them, right? And he was actually there in 5 or 10 minutes. But if we didn't have that on that building, how long would it have been before someone showed up at the building 2 or 3 hours later and you'd flooded the entire building? Yes, so that's one example, but there's so many other examples. There's so many failures that can occur. And with the diagnostics, it automatically identifies faults and sends it out to someone. It's really a great system. HVA efficiency tables. So you've seen these tables, and I'm sure you've looked through it. In fact, if I grab my energy code, if you have yours, they start on page C16, but they go on for page after page after page for all the different types of mechanical systems that we might have in the building. And what does it include? It includes their, for instance, computer room, ceiling mounted computer room units, ducted or non-ducted. It has different capacities, COP, return conditions, test procedures. They'll have efficiencies. They have all kinds of things which must be included on your equipment schedules so that you can see compliance. You don't have to understand everything what it says there, but if there's a certain efficiency requirement, whether it's an EER or an AFUE or some other energy factor, you can look through the equipment schedule. They should put them in your equipment schedule, and then you should be able to identify them. So we had all these tables, and they have added dedicated outdoor air systems. We'll talk about that in a second. Water source heat pumps, variable refrigerant flow, cooling and heat pumps, heat pump and heat reclaim chiller packages, ceiling mounted computer rooms, and air conditioners, commercial refrigeration and freezers. So they've added these tables to more accurately represent what's out there right now. You know, some of you have heard this before, and you've thought the same thing. Does it seem like the code is behind? Shouldn't this have been in the code before? Why does it take so long to get in the code? Because it takes a minimum 6 years to get anything in the code. That's just about what it takes. If one of you wanted to put something in the code, we didn't like something that we talk about today, and you called me up and you said, this is BS, we need to change this. We could write a proposal to put that in the code and submit it to ICC. And actually the energy code's kind of changed, it's a little bit more difficult. But generally the codes, you submit it. So if we submitted something today, what's the first code that it might possibly be in? The 24? 27 is the very earliest we would get it in. What's the earliest we would adopt the 27?
June 28.
29 probably, right? What are we adopting? We're adopting the 21 code on July 1 of 2023, right? So we would be, 2029 would be before it would be in code. So we're behind, but that's just the code development process. That's why we have ESR reports, or whatever you want to call the reports, to identify things that are new into the market and can they be applicable. The other thing is we can't address everything in the code. We simply cannot address everything, and we have to rely on the manufacturer's installation instructions, the design criteria and everything. So we really need to rely on our engineers and everybody on these bigger projects. So it's not that the code's stupid and dumb, even though it is sometimes, but it's simply the process takes that long. I've ran some code changes and I forgot that I ran them and they were in the code. You know, there was an amendment to the energy code that I put in, it was on the commercial side, that said, what the code said is the design professional is responsible in providing duct testing results or something. And Roger Hamlet at Colvin approached me. He said, Brent, why am I responsible for it? I don't do it. And so we just crossed out design professional and just said someone has to provide the pressure testing report on the ducts. Well, as they were reviewing the 21 code, we had this well, I made it a state amendment so that we took care of it in Utah like 6 years ago. But I got it through IECC back when we were doing the 21 code. And so when we were looking at the 21 code and going through the amendments, guess what we saw? That it was still there, and we didn't need it because I'd taken it out of the code. So it's a convoluted mess of a process, but just do the best we can. So I'm going to go through real quick. These are the tables, and I want to make a couple of comments, and I put a comment in green down here at the bottom, and so be ready with the microphone because I'm going to ask someone to tell me what the typical clearance is required between two condensing units when you put multiple condensing units in a row. Anybody brave enough to say in the microphone what most manufacturers say? Jacqueline, say 2 feet.
2 feet.
If you look at the manufacturer's installation instructions, and they're not all exactly this, clearances from a condensing unit stand alone. They'll usually allow 6 inches on one side and then want 12 inches on the other 3 sides, right? But if you look at it and you have 2 side by side, they want 12 inches for each unit. They want free areas, so some of them will reduce it a little bit and you don't have to have 24. Some say 18 or 20 or something like that. But you really need to look at the manufacturer's installation instructions because we have a whole bunch of them that are 1 foot apart. Is it a big deal? Well, if each one of them's a little restricted on airflow and a little less efficient, I think that one had 107 of them right there. We're building apartment buildings right now that have 300 and 400 of them sitting up on the roof. But because they're not installed according to the manufacturer's instructions, they are not as efficient as they could be. I was going to put a slide in and I didn't, but I've seen advertisements lately for these covers. Have you seen these to cover condensing units? Oh my heavens, do not, it's to hide them, and they're like big louvers that you stick all over them. They're going to destroy so many units, so if you see that, please don't buy one to hide your condensing unit. So anyway, this table tells us, depending on the size of the air conditioner, what the efficiency must be on the air conditioner. And it's already behind because guess what? A new SEER 1 and 2 standard just went into place, and so we have new SEER standards, so they're not accurate now. But anyway, so that's that table. Air conditioners, condensing units. Heat pumps, they look kind of the same, but the same type of thing. We have minimum efficiencies and the system they're tested by. Water chilling packages. What's the chiller? Why do we have chillers? And no one wants to take a stab at that one. There's a couple of ways you can do a building like this. A building like this, you really don't need a chiller. The largest one I ever did was a 4-story, I can't remember how many hundreds of thousands of square feet, but it was 4 stories, and we put 2 rooftop units, big rooftop units on it, 90 tonners, and we came down with 5-foot diameter duct. We entered with 5-foot diameter duct, and we went down through, and then we went out in high pressure duct to VAV boxes all over. So one unit did the top 2 floors, the other unit did the bottom 2 floors. And it took a lot of space for that 5-foot diameter duct to move down through 4 and 3 down to 2, where you could take it off and then reduce it when you went down to the first floor. But we were moving cooling We're moving cool air through these ducts, and and this was high pressure ducts, so it would have had been bigger if we were low pressure. At what point in time, well, it's about 4 stories, it's just not feasible to force air down through because it takes such big areas. So what's the better way to move cooling? With water. A 4-inch pipe can move a lot of BTUs, whether it's heat or cooling, or a 6-inch pipe or whatever, and it just doesn't take that much space. So chillers are air conditioners that we send chilled water out. We send the chilled water all over the building. You did some inspections at Gateway, Chris, because my first day at the city, I went with you and we went out and did some inspections at Gateway. And they have big central chillers that send chilled water to the whole project in a central location. You could not have a big air handler with ducts that are 15, 20 feet in diameter pushing cooled air all over the place. It's not feasible, but you can push chilled water a long ways. And so that's what we do. We use chilled water when we hit a certain size in the buildings. And so that's what we do with chillers. And a chiller, you can see they're rated, 600 tons. And, these are producing a lot of cooling. And so you will see chillers. And you'll see chillers cooled within cooling tower, and you'll see them that are air cooled like we have in that diagram there. So that's what a chiller is. And of course, it has some requirements, and you'd have to look them up, and I couldn't tell you off the top of my head what each one of those mean, but I've known at one time, I just can't remember exactly. Terminal air conditioners, or PTACs, we call these packaged terminal air conditioners. They're heat pumps, they're cooling only. We call them, there's PTAC, PTHP, which are heat pumps, and we have different sizes, what the efficiencies are required on each of those. And we even have those little things that go on the end of relocatable things that are vertical package air conditioners or heat pumps. Then we have a table for our basic furnace. And again, we have the efficiencies that are required there. We have boilers. And again, for the same reason, because we can push a lot of heat. With a boiler, we really have some extra capability because why? We can heat it. We can heat it a lot hotter. A chiller, we're kind of limited by how cold we can make the water. But with a boiler, we often are running them at 180 degrees, and we can move a lot of heat, and we even move steam sometimes. And there's just so much heat in that steam. But again, we have specifications for that. Heat rejection equipment. This is on the Adobe building down in Utah County, North Utah County. It's an evap cooler that's rejecting the heat from the chiller. So the chiller, if we back up, down here is what we would see inside a building. The compressors are on there. It has an evaporator section that is producing the cold water, and then the condenser end where we reject heat, pumps water to outside to the cooling tower, and we reject the heat outside of the cooling tower. Now, I'm explaining this because we have some code requirements that came into the 21 code on chillers and heat recovery in chillers. So they are basically big evap coolers. We run the water out through, it goes up into pads, runs down through it, there's a fan that's moving air, and we reject heat with it. And they use them all over the country. They use them in humid spots too. In our climate, you can take chiller water when it's dry outside. It can even be 80 or 90 degrees, but just running the water without the chiller have the pump run water through the cooling tower, and we can chill the water down enough by evaporation and take it in the building and run it through a coil inside and pick up heat or cool your building. We call that indirect cooling. The moisture, the evaporation is taking place outside, so we're not adding any humidity to the inside of the building. We're cooling it outside strictly by evaporation, pumping it in. And so we will have indirect evap cooling, which is just circulating chiller water. And then we can have direct evaporative cooling, where we have the cooler pads and everything in the airstream, but they add humidity. Anybody seen any of these stacked up? Rows and rows and rows. I'm getting mixed opinions on these. And I think a lot of them have to do with installation problems, but not all of them. They're challenging. If one goes down, they're expensive to repair. Where I took the picture of those air conditioners all lined up kind of close together, that was looking down on a lower roof of the same building. I could not get to that roof, but I don't know if those are installed according to the instructions or not. I don't know if those, I'm assuming those panels where they're butted together are solid and the air is coming in the other sides. But I'm concerned that maybe some of those are access panels or something. That's a big row of variable refrigerant flow units, isn't it? Again, we have all the specs for them. What are we doing with this? Someone is going to prepare a comm check, a mechanical comm check, and he's going to list, he or she is going to create a list and put it in comm check that identifies what the unit is, what type of unit, and the efficiency of the unit. And then we verify that the unit they're putting in matches the table. Computer room unit, kind of like the one I had on my opening slide. And this one was out at Facebook on this one. Same type of thing, ducted, downflow, non-ducted. Some of them just blow into the room, some of them blow down into a floor and then come up in all the computers. But we have coefficients of performance and such that are required on those. Vapor compression-based indoor pool dehumidifiers. Has anybody done a pool for a hotel or anything like that? Worked on them? What's your challenges with pool rooms? Obviously, it's humidity, right? How does a dehumidifier work? Actually, it's kind of cool technology. You have your evaporator on one side, your compressor, and then you have your condenser on the other side. Now, this is exactly how our air conditioner works. Our air conditioner, we have an evaporator inside, right? We evaporate refrigerant inside. We pick up heat. We send it outside to the condenser, where we run a fan to reject the heat, condense it back into liquid refrigerant, and then back and forth. So we catch with a standard air conditioner, we catch our heat inside, extract it, and send it outside. When that air gets cold, what happens? The moisture condenses out of it. So a dehumidifier works on the same principle. We take that evaporator and we might slow the fan down a lot so that we don't blow water off. We get it cold and we condense all the water out. But do we want a cold pool room? We don't want a 40-degree pool room, so we'd have to heat it back up. So with these dehumidification type units, we put the condenser right after it. So you cool it down, then you heat it back up with the heat that you used to extract the moisture. And then if you have excess heat, you send it outside. What's a better way to do it in Utah, and Arizona, and Nevada? I'm giving you a hint. Half of Texas. Anybody got an idea, a better way to to control that moisture? Carl's halfway there. He said ventilation. Heat recovery ventilation. What's a heat recovery ventilator? It's a ventilator, and we have a slide in here in a little bit. You take exhaust air out of your building. You pick up the heat in the wintertime. You pick up the heat from that air you're exhausting and use it to temper or preheat the air you're bringing back in. The problem with a heat recovery ventilator is that if you use it in humid parts of the country, you suck air out of your house that you've removed moisture from, that you've made a reasonable humidity, and you replace it with humid air. And so it's a problem. In our dry climates, we always said, well, let's put in HRVs, heat recovery ventilators. For our ventilation in our house, it's balanced. We exhaust 100 CFM, we bring 100 back in. But it does the opposite in our climate. I spend money to put humidity in my air in the winter time, and then I exhaust it outside. Then I bring in cold air and heat it back up from outside. What does that do to the relative humidity in my house? It tanks. It goes down. Because if I bring cold air in from outside, what happens? It doesn't have any moisture in it already because it's already condensed. You bring in outside air that might have 30% relative humidity, bring it in your house and warm it up, and it's going to have like 5% relative humidity because it has the ability to hold more moisture. It's relative to your environment. Heat recovery ventilators, though, in a swimming pool room, you exhaust all the humidity, you bring in dry, whether it's summer or winter, you bring in dry air from outside to replace it. You don't have to run a compressor, you don't have to do anything. They work incredibly well. Remember, Kirk, you remember out at the Kearns Oval, they covered that big pool. They covered a big pool and put in a heat recovery ventilator, completely controlled the humidity on a big Olympic-sized pool. So it's a good way to do it. But in other climates, this is what needs to happen, and there's no other way around it. And we'll talk a little bit more about heat recovery. I'm trying to explain how these work a little bit, so when you see them on a plan, you have an understanding of what's going on, or when you see them in the field. DOAS units, direct expansion, dedicated outdoor air system units, single package and remote condenser without energy recovery. What's a dedicated outdoor air system? We're building all these buildings that are tighter, and you build a set of apartments and you build it really tight, you might need to bring in some fresh air. In fact, you're definitely going to need some fresh air. If you're exhausting it with a fan in each unit, these are dedicated units. They're just supplying outside air, and you might duct it in and stub a 4-inch into every apartment to bring some fresh air in. And it's becoming more and more popular because we're making our buildings tighter, and we need to bring fresh air into the buildings. So there's air-cooled dehumidification mode type, heating mode. They're basically heating and cooling units. They're makeup air units, but they're dedicated to bring in outside air. DX means direct expansion. That means it's refrigerated. And we're seeing a lot of these. When I first retired, and I worked pretty much full-time for WC3 doing plan review, I saw lots and lots of these on large apartment buildings, and you've probably seen them on large apartment buildings because they bring what? Our ventilation air in. In our residential setting, we can put in an exhaust fan and exhaust it, and the code has allowed us to just rely on leakage to come in and replace that air we exhaust. We can't do that in the commercial side. We have to have some balance to it. If we exhaust 20,000 CFM, we got to replace 20,000 CFM, and this is one of the efficient ways to do it. It's just dedicated to that. It can temper it to the right temperature. And then we have dedicated outdoor air systems that have energy recovery in them, that do what we just talked about. They will exhaust a certain amount, but grab the heat in it. Now, I didn't finish my discussion on heat recovery ventilator. I mentioned how heat recovery ventilators just move the humidity whichever way. An energy recovery ventilator is a different animal, and I think some of you have heard me talk about these before. With an energy recovery ventilator, our heat exchange device is desiccant materials. And so what it does is it absorbs the moisture in the airstream. And so if you're in Biloxi, Mississippi, where I spend a year of my life, Jacqueline's laughing. Anybody been to Biloxi? It's not on your bucket list. I guarantee you it's not. I was in radar school there in 1971. But it's really humid there. So if we dehumidify our space, we exhaust, that air out of our space for air quality, and we have that air coming in that's humid. We don't want that humidity, right? We already talked about that. So as that fresh air comes in, it hits this desiccant material, and sometimes it's even a wheel, and you might have seen those. It absorbs the moisture. You bring your air in with less humidity, and then as the air is going out, it picks up that moisture and takes it back outside. So we capture the moisture and send it back outside. Well, in the opposite season, when we're cooling, in our climate now, it's actually better. I have a humidifier in my house. I want to maintain 30%. I put in an energy recovery ventilator. My moist air is moving to outside, but I don't want to give up the moisture, so the heat exchanger captures the moisture, the contaminants go out, and my fresh air coming back in from outside picks up the moisture and puts it back in my house. That's kind of a simple description of how it works, but it's kind of cool how they work. And they do work really, really well. So anyway, with a dedicated outdoor air system, we can have it also serving as part of our exhaust system. As some of that exhaust air, we're capturing the moisture, or we're to send it back outside, or capturing it to keep it back inside. And so ERV maintains humidity, inside humidity. ERV, energy, will move humidity straight through. There's no capture. And water source heat pumps. These are becoming more and more popular. Kirk, you remember when they built that community center in Mill Creek? They built a community center, and I think it was on Evergreen, and it was with water source heat pumps. So what is a water source? How do you work? I'll get it spit out here. How do they work? You have to have a water source to dump your heat to. So a water source heat pump will, in that case, they came into the project and they drilled 72 300-foot deep bores down in the ground, shoved loops down them, polyethylene pipe, I think it was, pre-formed with a 90 on the end. They buy them in rolls, 300 foot long. So they drill it, shove it down. They have can't remember what the grout is. It promotes heat transfer. 300 of them going down in the ground. So in the wintertime, the idea is we take a ground source heat pump and we extract heat out of the ground and use it to heat our building. In the summertime, we do the opposite. We extract heat out of the inside of our building and we dump it into the ground. Does that sound efficient? It actually is really efficient. Because why? If I'm running a heat pump in the wintertime, an air-to-air heat pump, So it's 35 degrees outside, right? Or something like that right now. I'm taking 35-degree air, running it through an evaporator on the outside and trying to extract some heat out of it. So I pull 35-degree air into it and I'm discharging 10-degree air or something outside because I've captured some heat that I bring in here. The colder it gets outside, the less efficient it gets, right? Because I have less heat. In the summertime, we do the opposite. We pull heat out of the inside at 75 degrees in here and we try to dump it outside where it's 95 or 100 degrees. It's not the most efficient transfer, but it works through refrigeration. Well, if I have 55-degree ground and I want to extract heat out of it, if I've designed it right, I've got a stable 55-degree environment that I can extract heat out of, and I'm going to get a lot more than I do out of 30-degree air or 10-degree air or whatever. Now, if they don't design it right, they can actually freeze up the loops into the ground because they remove so much heat they can freeze the ground. But done right, you have this good source. In the summertime, it's even better. You can have SEER ratings on ground source heat pumps in the 30s because why? We're taking heat out of a 75-degree inside environment and we're dumping it in a 55-degree environment in the ground. It's actually cooler. You could almost take and circulate groundwater through a coil and cool your house for nothing. It's not quite cold enough, but it's kind of interesting technology, isn't it? There's a lot of high schools and such and schools that have been built lately that use this type of technology. And we're going to talk a little bit more about it because they all hook into a central pipeline that's just circulating through the building and then going to the ground. And so you can take heat out of it, put it into that, take it to the ground, or you can bring heat out of the ground and bring it back. But what about, and think about this until we get there, what about if part of the building is heating and part of the building is cooling? The place that's cooling, you take the heat from the place that's cooling and put it in this place that needs heating. You don't have to send it to the ground. You just move it around the building. And so that's what's happening, and that's going to help you understand some of the code changes that just took place. Heat pump and heat recovery chillers. We already talked about that chiller. Have that big 300-ton chiller on a roof, and you're extracting heat from all these different offices and sending it out to the cooling tower and send it outside. Well, with a heat pump or heat recovery, we do the same thing. Rather than send it to the cooling tower, if some places need cooling and some places need heating, we just send the heat to the places that need heat. Let me explain it a little bit different way. You have a big office building, and I'm looking at building over here, and even this one's probably not quite big enough, but you have a big office building, and it's winter time. Do we need heat in the middle of the building? We don't need any at all. Where do we lose heat? In the wintertime, where does heat go? Heat leaks from it is transferred through our walls. It's conducted through our walls and our windows to outside. So we need to heat the perimeter. And in fact, when I did that building down on State Street with the 2 90-ton units, we only put heat on the VAV boxes around the perimeter. We didn't have any heat in the interior. Because if you heat the perimeter, how does the center get cold? It's not. In fact, what's going to happen to the center of the building when it's 0 outside and it's occupied? It's going to get hot. Why? Bodies, computers, printers, everything that's taking place inside the building. So every large building that's in operation right now, in our conditions right now, is cooling in the middle and they're heating on the perimeter. And so what this technology does is says, well, we're not going to cool this and dump it outside. We're going to use it where we need heat. Now here where we live, We use economizer and stuff for a lot of that cooling, so it's free cooling. But when you're in a humid climate, that doesn't happen. So this is really important in a humid climate. Ceiling mounted computer room air conditioners. These are literally fit in a ceiling grid. You have a little small room that you have a couple of servers in it. You can put in one of these units up there in the ceiling, but it has specific efficiency requirements that you need to comply with. Supplemental heat. Since we've been talking about heat pumps, everybody understands a heat pump just pumps heat, whether it's bringing it in from outside or taking it from inside to out. And in the summertime, in the wintertime, we do have situations sometimes where you can't get enough heat. If you have a poorly insulated building, you're going to need a lot of heat, and the heat pump just simply can't keep up with the demand. And so we have what we call auxiliary heat. So at some point in time, it can't keep up, so we need to add some auxiliary heat. There's two ways you can do it. You can add auxiliary heat by adding heat in the airstream of the air handler. So we're adding some heat from outside, but we don't have enough, so we turn on some strip heat inside the air handler. What do I mean by strip heat? Anybody know? Like a toaster. Just coils. Not the other kind of strip, Chris. Sorry. So it's toaster elements, basically. And you can put in 5 or 10 kW of heat strip. Is heat strip very efficient heat? It's horribly inefficient. A good heat pump will give you 3 BTUs of heat for every BTU of electricity consumed. We call that a coefficient of performance. So as that heat pump's running, when we compare it to strip heat, we're getting 3 times as much heat from that heat pump pulling heat from outside. We're just transferring heat. We're not converting electrical energy directly into heat. So if you have a heat pump that just can't quite keep up and you have heat strips, you don't want the heat strips to kick on until it absolutely is required. Does that make sense? You don't want them to kick on until you absolutely have to. Well, thermostats for years and years and years have operated heat pumps with what we call 2-stage thermostat. So you set the thermostat at 72 degrees. The heat pump is running and running and running, and it's just not quite keeping up, so the temperature drops a little bit, and it drops down to 71 degrees. Thermostat says, well, we're not keeping up, we'll turn on the strip. So it turns on the strip runs until you get back up to 72, and then it shuts off. What happens if you go to that same thermostat and you decide you want to turn it up to a warmer temperature? You know, you come in, you're cold, you want to turn it up. So you turn up 4 degrees. The strips automatically kick in, and the strips are going to run till you get within, for instance, 1 degree of set point. But what if it was warm enough outside that the heat pump could have got you there? So that's what this code section is saying, that supplemental heat, if it's electric strip heat, cannot turn on until the heat pump can't keep up. That's basically what it's telling us. And it makes perfect sense. Most units come with it right now. It's some form of outdoor thermostat or something like that. What are we seeing now more and more? Maybe those that come in and get a permit for a furnace replacement or something, you might have seen these. They recognize that the house can't keep up with a heat pump, and so they add, instead of just using an air handler, they put in a gas furnace, they put in a hybrid system. And so it runs on heat pump as long as that's efficient and can keep up, and then you hit a certain point and it shuts that heat pump off and turns on the gas furnace. And we're seeing a lot of those going in right now. Depends on your application and what you need to do. Okay, a change in,
I have a question about that.
please, where's the mic? She just walked out, didn't she?
I'll kind of make it loud then. Is there a climate zone threshold for that hybrid system being a good idea?
Question is there a climate zone? When's the right time? When is the right climate when you put in that type of system? It kind of depends on, some of it depends on the house. If you have a house that is not very energy efficient, then they're probably a really good idea. You see what I'm saying? Because the colder it gets, the greater your heat loss, and with a poorly insulated house, your heat loss really goes up. And so those types of situations. I'm toying right now, I just can't decide what I want to do on my house. I have a 2-story house with a basement. It's not as bad as someone had the 6-level house that's on a single system. I have 3 levels on one system. I didn't put it in, I bought it that way. And I'm really, really thinking about doing some of these multi-head heat pumps. You know, where you have one outdoor unit and I have 3 or 4 little air handlers inside. But my wife is not very comfortable because she's heard me complain and everything about heat pumps over the last 50 years, especially when I was wearing tool bags and you had to go outside and it was 10 degrees and you're trying to work on a heat pump outside. So I'm thinking about doing just my top floor and putting a master bedroom zone. And I'm going to use you can put a little ducted air handler on them that just has 3 or 4. Putting one in my master bedroom, maybe catch the laundry off it, put one for the other 2 bedrooms, and then one for the bonus room that I'm going to add on the other end. And maybe even break the bedrooms up because one's north and one's south, so that I have individual control in each one of them. But I thought I'd start with the top floor. My house isn't perfectly insulated, it's pretty good. If I start with the top floor, that's where I need the least amount of heat because I have heat from the other system coming up. But I'm not sure if it'll keep up with my basement. So, and I know you're thinking about doing something with heat pump, I think you said. And so if if it doesn't have a huge load, then you don't need to go with the hybrid system and gas and everything else. You'll alert me when lunch gets here? Okay. Okay, there's a lot in there. We've already talked about controls and building management systems and everything. And again, we're talking about big buildings, and so all this stuff doesn't apply to that little dentist's office or whatever that we were talking about, or the convenience store. But you have a large building that shuts down at, let's say it shuts down at 5 o'clock or 5:30 at night. They've found that you can save a lot of money if you let it coast to off. So let's say you leave at 5 o'clock. The system, the logic in the system decides, okay, how early, and there's some set points you can set, how early can we shut it down prior to 5 o'clock? People are getting ready to go. Can we shut it off at 5:15 and it's going to take, 4:45, and let it coast to where at the time everybody's leaving, we are starting to drop down where we'd want heat again or cool again. So you say, well, is that a big deal? Well, it can be a big deal. Well, you saw what an efficient building costs for electricity in a month. You know, some of these things that are built into the building management systems, all it really costs is a little bit of programming. They're pretty slick ideas. And if you take a bunch of these little ideas and you add them on top of each other, what do you have? You have an efficient building. But that's in the code, that when you hit certain sizes on buildings, your controls need to, optimize the stop schedule. Okay, we've talked about the cooling towers and how we're rejecting heat with a chiller through a cooling tower. And here's a cooling tower you see in the diagram. See how you have the big fan and we're circulating water through the tower. This one's a closed circuit. Some of them, the actual water is going, the water in the tower is going outside. You can see this one has a heat exchanger in it. So we cool the water, then we have a heat exchanger. So this is what we call a closed circuit cooling tower. So the water that sees outside and all the contaminants outside never goes in, and you're able to keep cleaner transfer solutions running through it. But there are times a couple of things happen. If we have that loop for a heat pump and we just want to reject heat when we don't need it someplace else in the building, if we don't have pumps shutting down or check valves closing, we actually have heat migrating up and disappearing to outside anyway. And so basically, this change in the control says that we don't want to reject heat to outside through a tower when the heat's needed in the building. So if there's a heating demand in the building, you need to really lock it off so no heat can, through pumps and valves, so that no heat is rejected that we want to maintain inside the building. Variable refrigerant flow. One of the big things about these is we have all these little air handlers scattered all over the building. How do you get fresh air to them? You know, when you have a standard big penthouse air handler, and I don't have a picture in here of one, I should probably grab one. You go on top of some of these roofs. In fact, maybe we ought to do a field trip to one of these sometimes. In fact, when I was teaching here, we went up and did some field trips in some of these. You have a big air handler that's built on top of the roof that's just massive, and you'll have big hoods that are bringing in outside air. It's controlled by dampers, and they'll be bringing in a certain amount of outside air for ventilation, and then you'll have power exhaust. Someplace else is exhausting air out of the building. And so they're ventilated that way, and they are economized that way. When I say economizer, I think most of you know economizers are, it's this temperature outside. We need cooling in a building because of all the internal loads. Let's just bring in some outside air, mix it in with our supply air, and we can cool for free. Well, how do you do that with these variable refrigerant flow systems that don't have a duct to outside? You need some type of fresh air component and, in some cases, an economizer to it. The code has recognized that's unique, and if you have a dedicated outdoor air system that can provide your ventilation air and possibly provide some economizer action by bringing in some of that cool outside air, then you don't need to worry about economizers with the variable refrigerant flow systems. If you haven't seen it, that picture that I had a whole line of them, this picture with a whole line of them, those are going inside, and one unit is serving multiple air handlers in different locations. Demand-controlled ventilation. I don't know if I'm going to ask if anybody's brave enough to tell me what demand-controlled ventilation is. But this room right here, how big do you think this room is? Chris, you're good.
Talking about cubic feet or?
Square feet. Yeah. How much? Close to 1,000. It's over 500, isn't it? Okay, so we have a space. It's over 1,000 square feet, and the trigger, there's a 500 square foot trigger in this, I believe, if I recall correctly. But what the code has had for a little bit is what we call demand-controlled ventilation, and it's basically saying we have a room right here, and we have 12, 15 people in it. When the room's vacant, how much fresh air do we need in the room? None or very little, just enough to keep the air freshened. This is, I'm assuming, on VAV boxes. In fact, I'm positive it's on VAV. Has a plenum ceiling, there's the returns. So we load it up with people. Do we need more ventilation? We do. I've used this example before because it's such a perfect example. I've got a neighbor that's 3 doors down from me that plays the organ at church, at the church around the corner. And she goes over during the week. She doesn't have an organ in her house, so what does she do? She goes over in the week and does what? She practices. Where's the organ? It's in this big chapel that has an occupant load of 300 people. So the system is designed to bring in enough ventilation air from outside for 300 people. So Sue goes over to practice the organ and hits the thermostat to turn on the system, to heat up the room for her, and it's bringing in thousands of CFM of fresh air from outside because it's bringing enough air for 300 people. Is there any logic to that? But that's how it's been for years and years and years. Well, with the advancements in systems and control systems and everything as we're talking about, we have in this room, there's a sensor right there that I'm sure is hooked to the building management system. It's hooked to a VAV box up in here that has these 4 supplies on it, and it's independent of other rooms. This room has its own climate. We have air coming from the roof, and it's circulating around the building all the time, and as that VAV box opens up, we add some air to this space. If it needs some heat because it's on the outside, then the hot water coil, the valves open, we put heat to the coils. Well, that VAV box has some fresh air in it. A certain percentage of it is fresh air from outside. And so with this room in an education type setting that has the potential, it does meet the requirement, because we can definitely get more than 15 people per 1,000 square feet in it. We need to increase the ventilation air when we get a number of people in here. So how do we do that? Do we count? Is there sensors up there that are counting how many bodies are in here? There actually is kind of a sensor up there that's counting how many bodies in here. What's it measuring? Carbon dioxide. So based on the amount of carbon dioxide that it's sensing being discharged into the room from us breathers, it modulates the ventilation air. So demand-controlled ventilation with newer systems, it's really not a difficult thing, but it needs to be provided in rooms where you have that condition happening. There's classrooms all over in this whole area. We don't need ventilation for the whole building like every room is occupied all the time. We can do it on demand, and so we do it with demand-controlled ventilation. And it can be a sensor on the wall, or it can be a sensor in the duct. The fan's always running. We just sense. It's probably, I don't know if this building has it because it was built before, but it could just be a CO2 sensor right there in the return that's sensing what's going on in this environment. It's actually pretty slick, isn't it? It's available on rooftop units, little small rooftop units. You guys have seen them, 2 and 3 and 4 and 5 ton rooftop units. There's actually logic and everything on them where you can put that on it. And it now includes retail sales areas where you can end up with that type of density. And there's a bunch of exceptions to it that you don't have to do it. Multiple zone system with design airflows less than 750, where you have a lot of air coming in anyway. So a place you would not need it would be in a nail salon that needs a lot of air anyway, or a beauty salon, because you're having to bring in a lot of air anyway. So there's really not any need there because you have to have you have a big makeup air requirement. Spaces with one or more of the following occupancy classifications per table 403.3.1.1. Those are familiar with the mechanical code knows we have all these tables. It's like 6 pages worth that tells you, of all these different building uses and how much ventilation area you need. And so any of these locations here, correctional cells, barber shops, beauties, and nail salons, bowling alleys, all those they simply need a lot of air. That finishes demand controlled ventilation. We'll break for lunch. Why don't you grab your lunch? I'm going to probably start up about 12:30. And if you're not done with your lunch, you can finish, at that point. So those online, we'll see you around 12:30, 12:35. Welcome back. If you're here in the group, feel free to grab you a little more food if you want, and we'll just proceed. So we ended talking about demand-controlled ventilation. Are there any comments or questions anybody has before we move on? I know we talked about a few things at lunch. But if not, we're going to move on. As you can see, a lot of what we've been talking about on the mechanical is on the control side. And how we control our systems makes such an impact on how efficiently and effectively they operate. And one of the next things that makes a difference is our parking garage exhaust systems. And I think if you're worked around these, you're fairly familiar with. We have requirements in our parking garages that include sensors that when our carbon monoxide or nitrogen dioxides hit a certain level, we increase or we trigger ventilation in the enclosed parking garages. If we have openings around the sides that'll allow it to ventilate by itself, we don't have to do that. But there's a lot of big fans that are just running continuously on parking garages, and they run all the time in case, they're needed. Or they stay off for a while and then they turn on, or they're running in various parts of the parking garage. And what the code has over the last few code cycles recognized is, number one, you need more efficient fans on your parking garages. For many, many years, we didn't have any requirements on how efficient the fan was, if it had variable frequency drive or whatever. You just put in a fan, and then you might run it at one speed, and then when it triggers, it goes to a higher speed. Or some of them just shut off until it's sensed one of those contaminants. And let me back up just a little bit. At first, we just sensed carbon monoxide. Now we sense nitrogen dioxides because they're more prevalent in diesel. So what the 21 code has done is recognized the value of demand-controlled ventilation inside buildings and applied the same logic to parking garages. And so that we modulate fan operation, exhausting, based on our carbon monoxide levels and our nitrogen dioxide levels. And so that's what the change is. And we had a threshold before of having to have this type of technology at 22,500 CFM, and it's now dropped to 8,000 CFM. And the size of that system is going to depend on the mechanical code and how you size those systems. So it's demand-controlled ventilation for parking garages. Chris?
How do you test those sensors?
How do you test sensors on
CO.
CO detectors? Those systems, in fact, that's been a hotly debated item in code change because there's several people maintain that they never work. Well, what the code has done is it's mandated in the design of the system, and the standard for those systems is they have fault detection in them. And if they fail, they go to full on, and there's an alarm on it that shows that they failed. So now the older systems aren't going to have that. My experience with them is the biggest problem with those is the improperly located the sensors. You know, when you do a plan review on a parking garage, we have a diameter. It's kind of like doing an ADA thing where you draw 5-foot circles, where you draw 25-foot or 50-foot circles in your, you don't do it, but your design professional should, to identify the coverage in the whole parking garage, that wherever a sensor is located, we make sure we have coverage in every square foot of the parking garage. And I noticed a lot of that, 2018 through 2020, I was doing a lot of reviews for WC3, and a lot of them were in California, but very often that they just threw in some sensors, and I required them to identify the coverage, by drawing it on the plan, showing that they truly had coverage. But I found, I worked on a lot of them. I installed some. They work really quite well. And I think even some of them have a test button on them, like your smoke detector that you, but, I mean, have you had experience where you don't think they were working, or?
Well, I don't have Mike. I just remember a long time ago, I had this one guy had a gas generator.
She's bringing it to you.
A long time ago, I had a guy with a gas generator, and he pulled a piece of visqueen around him inside the generator with the sensor, and he turned on that generator, and it was just running a whole bunch of byproducts, and the fans never kicked on. And I was just like, I don't want to see another guy do that.
That's crazy. Everything, and I'm trying to remember the last time I looked at one. It's probably been 2 or 3 years, but they had built in them, diagnostics that could tell that the detector, there's some type of self-test that it ran that the detector was working. I think the ones built today are probably pretty good. Something I'll look into. A good question. Energy recovery changes. In some cases, energy recovery is required in residential apartments. And there's a lot of exceptions and such. Excuse me. And it doesn't apply in some climate zones. It does not apply in 3B, which is part of Utah, that's Washington County, unless ventilation air exceeds 30% of the design airflow. Bottom line is, for most of what we have in our climate, there's an exception. You have to exceed 30% of design airflow, and 30% of design airflow is a lot of ventilation air, and we just don't have that. I mean, if you had a condo that had indoor spas and stuff like that, then that would trigger that, but our typical isn't. On here I have a diagram of a energy recovery ventilator, and I don't know how well you can see, but you see the white arrows are the fresh air from inside going to outside, and then the red arrows are the air from fresh air to inside from outside is white, and red is from inside to outside. And so in the center there, you have this heat exchanger that actually when the door's on, it seals on this center panel here. And so air is going in through the exchanger and this way, where the other air is coming in through this one and going the other way. And it's a heat exchanger that doesn't allow the air to mix. You know, they have to pass, they're passing one on top of the other. And they have efficiencies between 65 and 85, 90% efficient where they recover that much of the energy from it. And it works both heating and cooling. In the summertime, we're throwing away cooled air, and we can use that cooled air to remove heat from the outside air coming in. And in the wintertime, we do the opposite. We're throwing heat outside. We use that heat to bring the temperature back up on the fresh air that's coming outside, that's starting cold, and we warm it up with that waste heat. This is a desiccant material that absorbs moisture, and so this one's an ERV. Hotel guest rooms and ventilation controls. There's just a little bit of clarification that went on. There were not any changes on the lighting side, and so we won't talk about that when we get into lighting. But the changes are on the HVAC side and on the ventilation controls, clarified how it's to operate and reducing sensor shut-off from 30 down to 20 minutes. So it needs to shut down within 20 minutes of when the occupant leaves. And again, those can be controlled centrally. They can be controlled individually in the room. I don't know. I guess maybe when people learn them a little bit better, the hotels won't have so many problems with customer complaints. And I think that's the big problem is if the customer understood what was going on, they wouldn't have to give them keys and say, just put it in there. But people just don't understand what they're doing. Okay, let's go into some additional definitions. There's a definition for a fan array. It's multiple fans in parallel between two plenum sections in an air distribution center system. So I don't know, how many have spent some time up inside a penthouse, a big air handler? What we've seen, we see some big fans sometimes. I mean, that job that we did back in the 90s, we had, I can't remember if we had 50 or 75 horsepower motors on the fans, so it's a big challenge. They really are. But it's becoming more and more popular nowadays to put fan arrays in where we have smaller fans, and we just put a bank of them in there. And this is at Facebook, and I think it's worth discussing a little bit about what they did there. It's about 1 million square feet of data center, and the building's kind of shaped like an H, and it's 1,250, almost 1,300 feet long on each leg of the H, and so it's data center all the way down for 1,250 feet. On the main level, and then up top is air handler. That's all it is. It's 100% air handler above it. The cross in the H is the administrative section that has conventional systems. But for this huge data center, they're using nothing but 100% evaporative cooling. There's no chillers whatsoever. Now imagine what the chillers would be for a row of servers that is 2,500 feet long, and because that's what it is, 2 legs of, and it's just huge. If you try to look at the right picture, you can kind of see that this fan array just kind of disappears down to a door, and so there was a little spot in the middle, and so we had around 600 feet on each side a fan array set up like that. And this is pulling air in from outside. And you can see these are about 3 to 4 foot diameter fans. And the view here, you know, they're encapsulated in plastic still, but you can see the blades on them, and each one of them has the motor on the shaft. Is there an advantage to having the motor on the shaft? I mean, the fan on the shaft of the motor? direct drive, no belt loss. You know, you're 100% put all your energy in turning the fan blade. You have bearing losses in the motor, that's it. And they're all, of course, controlled by freak drives, so they can vary up and down. And you have a whole bank. If one goes down, you get a diagnostic that you have a fan down, and you can go take care of the fan. So here is that fan array. And here we see these panels. Anybody ever have a cooler that had cell deck material in it like that? The Master Cool swamp cooler, you ever seen those? They have a big manufactured media like that, and then you move water down through it. So these run down the same length, the whole building, and every so often between them there's a space, and you can see it in here. So you'll have a V of cooler deck, you know, cell deck cooler material, and then you have a damper beside it. Why would you have a damper beside it? Because you don't always need the air going through the cooler pad, right? Like right now, they don't need the coolers operating. The coolers are not, you know, there's no water going through them. They're modulating dampers and bringing outside air through. This upper view here, you can see it from the other side. They have infill that they had to do down below. So there was two 600-foot long sections that they had all this cooler pad running all the way down there with a set of fans that pull it in. It dumps down in between the rows in the data center, between the rows of the racks of computers, and then the return side, which is basically just exhaust going outside, comes from the other side of the racks. You know what I mean? So you had a hot aisle and you had a cold aisle. It's actually a pretty amazing thing. They did have to, I don't know what they did for water, but they said they had the water covered because they are using some water, but they have water treatment and everything, so they're not wasting any water. Water that isn't evaporated goes down and is collected. This is a savings of, I'm sure, millions of dollars a year in cooling expense because they did that. And it does have the fan array on there that meets the definition in the code. And fan arrays are becoming more and more popular because they are so much more trouble-free and they don't have the vibration and the noise problems that you have with huge, large fans. Another definition is a fan in an embedded fan or fan embedded. And that's a fan that's part of a manufactured assembly where the assembly includes functions other than air movement. So what is that?
That's your garage.
It's my heater in my garage, right? Is-
You showed that a couple times.
I don't know. I think I just took this one.
Yeah, okay.
Is that an embedded fan?
I don't know, is it external?
It's part of a manufactured assembly where the assembly includes a function other than air movement. So a box fan or a fan like on the end of a chicken coop, its purpose is just air movement, right? So it wouldn't be considered an embedded fan. This is an embedded fan because it's just a component in a device that's doing something else. It's heating. It's more than just air movement, it's adding heat to the air. The reason that a lot of these definitions got added to the code is because the code really is coming down and really focusing on fan efficiency. But they want to make sure it's clear that you're not going out on a rooftop unit or you're not going out on a unit heater and checking the efficiency of the fan. The fan is an integral part of a system that's doing something else. It's been rated with the efficiency of the unit. We don't want to be involved in second guessing the fan that the manufacturer put in it. Now, the tables that we went through before that manufacturer had to meet a certain efficiency, and so he's already had to do things with the fans that are built into that rooftop unit or whatever. This manufacturer's already had to look at that. It's a low horsepower. It's probably a 10th horsepower or something like that, so it doesn't need much more. But anyway, a lot of these things are just to add clarity. Those of you guys that work in plan review and inspection know that you read through the code and invariably you come up with a situation that isn't addressed in the code all the time, right? And we just need to clarify that. And so that's what a lot of these things are doing, is clarifying. Fan energy index, and this is kind of what we've been leading to. It's the ratio of the electrical input power of a reference fan to the electrical input power of the actual fan is calculated in accordance with this standard. So it's basically a way of rating the efficiency of the fan. Now, those pictures from Facebook, are those embedded fans? No, they're independent. You know, that's a build-up system. We have fan arrays, we have cooler pad, we have dampers on outside that open and close. We have all these different components that we've integrated together to create a functioning air handler cooling system, but they weren't built as an assembly, so each one of those needs to meet the requirements of the energy code. Fan nameplate electrical power. And these are all things that are identified in the code that we need to check on for our fan efficiency. And it needs to be stamped on the rating plate on current fan assemblies. And so here's what we have: the fan system electrical input power, the sum of the fan electrical power for all fans that are required to operate at fan system design conditions to supply air from the heating and cooling source to the conditioned space and or return it to the source or exhaust it. So in a nutshell, that's all the components that in that Facebook building, and that's what we have here, that went into it. So we have the fan array here that is bringing the air in from outside here on the far left, through here, and there actually filters went in on that side, through here, through the cooler, down through the ceiling, the floor, the ceiling of the data center below, through all the equipment, back up, and exhausted to outside through those larger fans on the other end. And so that fan system electrical input power is all the power by both of those fans. And you could have in an office building application, you could have power exhaust fans, and then you have the fan that is circulating the air around the building. Here we don't have that. You know that diagram I had at the very first, the mechanical section where it showed all the controls and it had the picture of the computer screen? We had a fan that was exhausting out of the return. We had a fan bringing air in from outside, and then we had another fan that's circulating air around the system. It all adds up to just a lot of electricity, and so everything we can do to make that efficient. And so we get down to the code. Each fan and fan array shall have a fan index not less than 1 at design operating. Each variable air volume system, VAV system like we have on here, have a fan energy index of not less than 0.95. I don't expect you to remember all those things, but what I'm hoping to do is introduce you to this stuff, so when you have a big project come in, you know you're going to have to worry about controls, you're going to have to worry about fans, you're going to have to worry about all these different components, all related to the energy that we're consuming. And then we have our whole list of exceptions, and they're always there. And I'm guilty as the next person of not, I read something through and go, oh, they have to do that. And then you look at the exceptions, And if it's less than a horsepower, if it's not embedded, if it's embedded, if it's less than 5 horsepower, multiple fans in series or parallel combined at less than 5 horsepower, and then fans and equipment in the tables. And what tables is that number for? That's all the tables that we had the efficiencies, right? We had the furnace, we had the chillers, we had all those things, and what it's telling you is what I just said, is that we don't worry about those because they're part of that manufactured assembly. Fans and equipment certified for energy performance. Ceiling fans, non-portable. You know, the big fans we have hanging from the ceiling. Fans moving gases above 425. Fans in explosive atmospheres. Reversible tunnel ventilation fans. Emergency only conditions. And then out of the scope of the standard that rates the fans. And this is in both the residential and the commercial code, and it's actually been adopted in Utah. In the 2018 code, if you look at the state amendments, when we adopted the 18 code, we actually adopted this table for residential. It's also in commercial, but you heard me earlier mention that if you have a single-family dwelling, you can exhaust air out of the master bathroom and let leakage replace that air, and that be your ventilation system for a home. If you have a big apartment, you can have fans in the bathrooms, and most of the new apartments that you see nowadays, they're putting a fan in the bathroom. They're hardwired, they just run all the time, and then they're providing makeup air to the building through a dedicated outdoor air system or something like that. You can't go down and buy that cheap piece of crap at Home Depot that costs $14 and put it in, because why? Because they're horribly inefficient. You have a standard here, or a requirement in both commercial and residential code that specifically gives you a CFM per watt requirement. So an HRV, ARV, airflow, any airflow rate, the minimum efficacy CFM per watt is 1.2 CFM per watt. Where if it's an inline fan, it's 3.8 CFM per watt. Bath utility fan, 2.8. Bath utility room, higher CFM. The first one was 10 CFM minimum airflow. The next one's 90 CFM minimum, 3.5 CFM per watt. Why did they allow the HRV, ERV to have a less efficient fan? You notice that? It's 1.2 CFM per watt, where all the others are almost 3 or higher. Any idea why that's happening?
Well, because you're trying to recover. The recovery nature of the appliance.
The recovery nature of the appliance, yeah, you're basically there. What happens with the other fans, if it's a bath fan, you have a fan and a duct outside. With a heat recovery or energy recovery ventilator, what do you have? You have a fan, ducts from outside to inside, inside to outside, and you have a heat exchanger you have to flow through. So you know you're going to lose some efficiency in moving air. You're going to have a little more fan horsepower to pull it through the heat exchanger. And so because of that, you're going to be less efficient. Anyway, that's on everything. And these are becoming pretty popular. You walk through Costco over here, and you might see a fan that's $90 or something like that sitting there that's normally $120 someplace. That's a high efficiency fan that would fall into the 3.5 CFM per watt. Has anybody put in one of those high efficiency Panasonic or other brand fans?
Yeah,
Can you hear them?
very quiet.
Extremely quiet. They have a real good design to the fan blade, don't they? They aren't just this little cheap piece of plastic that's just beating the air out of it. Like,
Sometimes you have to enlarge your outlet.
You have to enlarge, and the duct going outside, you might need bigger just so that you don't have resistance. But yeah, some of those draw, on low speed, they draw about the same amount of power as a doorbell transformer. They're very, very efficient. I bought one, and I opened it up, and I had it sitting on the island in the kitchen, and I put a cord on it and plugged it in, and it was sitting there on the counter, and my wife says, "Wait, you gonna put that away?" I says, "Yeah, in a minute," and a few minutes later she says, "Wait a minute, that's on, isn't it?" She had walked by it and felt the air blowing out of it, but you couldn't hear it. It was on a lower speed. You take it all the way, I think mine goes from 50 to 120 CFM. At 120, you can slightly hear a little bit of airflow, but they're extremely quiet. No one's going to be complaining to that noisy fan or anything like that, and they're just very efficient. And they're low-capacity ventilation fans, but they play a big role in maintaining our air quality in our dwelling units. Duct plenum, insulation, and sealing. And maybe, I don't know if, Chris, you've called me on that. I know people have called me from just about every jurisdiction in the Wasatch Front about underground ductwork. Does it have to be insulated? Have you ever encountered that, Chris? Or
I don't recall ever seeing it insulated.
okay. Well, the question is, ducts outside the thermal envelope have to be insulated, right? If you have it in the attic, it has to be insulated. If it, basically, the code says if you're outside the thermal envelope, you have to insulate the duct. And I've had a lot of people call me and say, well, do I have to insulate the duct? Then I put under slab. And my first question is, where's the thermal envelope? Where is the thermal envelope if I have I don't care if it's commercial or residential building, where's the thermal envelope on a slab-on-grade floor? But I thought the thermal envelope was defined by where you put the insulation.
Yeah, but it's not an insulated floor.
I'm sorry?
It's not an insulated floor.
It's not an insulated floor. I'm playing devil's advocate here. We build a house with a basement. Where are we required to insulate? We insulate down the basement walls, right? Have we ever insulated under the floor? No, the only time you might insulate under a floor is if you put radiant heat in the floor, and then you'd have to insulate under the floor. Slab-on-grade commercial building. You insulate around the perimeter, right? 2 feet. 4 feet if you're up there in the Wasatch County. Isn't the thermal envelope around the perimeter? No one can give me a straight answer, and it's been up for debate. I maintain that, yes, we might have a little bit of heat loss from that duct into the ground, but the ground is 55 degrees, 60 degrees. It's not outside, and so if we do have an insulation requirement, it should be less than what the commercial code says, what, R12. And I've seen them go in with insulation. I've let them go without insulation. How do you insulate underground duct? Spray polyurethane foam on it? How much is that going to cost you?
Me, nothing.
You know, I've seen them try to wrap that bubble stuff around that's really kind of garbage anyway and doesn't give you any R value unless you have some airspace on it. I've seen a lot of things. This took a while to get in the code, but Jay Peters out of New Mexico is a consultant. He was with IAPMO, then he was with ICC, and he has worked in mechanical his whole life. And he represented this company called Blue Duct on their product, and it's a plastic, cellular core type plastic duct. And he maintains that we just don't have that much heat transfer from a duct in the ground into the ground. And I kind of agree with him. And so they found a standard, I think it was in the NSF standard, but whatever, they took their blue duct and they did a test, and they put 100 feet of duct, and then 6 feet over whatever, they put 100 feet of their product, and then they put 100 feet of insulated duct. They moved air through it, the same temperature, and they called it thermal distribution efficiency, and measured the temperature, entering temperature and the outlet temperature. That was basically the same. So what does that show you? It shows you with whatever minor amount of insulation effect you have from that cellular core PVC type material, you're not losing appreciable heat out of the duct. And I think if you did it with any type of system in gravel, that you're not going to have that much heat transfer through it. You know, I've had people argue with me, well, if you fill the whole thing with gravel, you have air spaces and everything, and isn't that kind of insulation around it? I don't know. I guess the best thing, if I was putting an underground duct system in, I would go to this system, and if you're using sheet metal, you know, the PVS, the coated spiral pipe, maybe you need to put insulation down under first and lay down insulation under. And guess what? When you get into the code now, then you have to debate, and the code hasn't clarified it, is this a heated slab? When we say heated slab, what do we consider a heated slab? Radiant heat. Is this a heated slab? And we don't have clarity on that yet either. Because if it is a heated slab, then we really need to have insulation underneath it. Yeah, but it would have to be underneath it. You couldn't put it on top like you would for radiant slab, because our heat source is underneath it then.
Isn't radiant, the insulation below the radiant?
Yeah, it's below what I,
Below here too.
if you put the insulation underneath the pipe. What I'm saying, before you do any backfill, put down your 2 inches of foam and then just do everything on top of it. And then we definitely know where our thermal envelope is. I'm just throwing it out there for discussion because this is something that the code really still hasn't addressed very well. Let's take it one step further. If it's a cooling only system, do you need any insulation under any condition? You're shaking your head no. And I agree with you, because we have also in the code, and I think, no, I didn't put it in. Oh, it's on this slide. What does it say right down at the bottom here? When design temperature difference between interior and exterior of the duct or plenum does not exceed 15 degrees. So if you're in cooling only, you have a cooling only duct system under slab, when the system is in cooling mode, what's your air temperature in your duct? Probably, most likely, it's 20 degrees cooler than room temperature. So that would put you someplace around 65, 60 degrees. Is your air temperature going through the duct. That's your cool air temperature. It's always somewhere around 20 degrees cooler than your return temperature. Your return temperature is set point temperature. You're somewhere around there. So if we have 65 degree or 60 degree, excuse me, or 55, 75 to 20 degrees is 55. If we have 55 degree air moving through the duct, what's the temperature of the ground? 55. And so even if we're off a little bit, we're a little warmer up top or something, our ground is pretty much 55 degrees. Maybe it's 60 degrees. Do we have any temperature difference? We surely don't have 15 degrees, right? So in that case, we don't need any. Under any circumstance, we don't need any because of that exception. Leave my drink over there so it doesn't end up in my computer. Pipe insulation. And I don't need to read through all these. We do have a state amendment that I completely disagree with that says that on the residential side, that you don't have to insulate hot water pipes that are underground. And that's because the plumbers in St. George complained of how expensive it was for them to insulate all that pipe that they run underground when they build all that slab-on-grade stuff in St. George. But I guarantee you, I mean, it's building science, that a pipe in the ground loses heat at a rate 4 to 5 times greater than a pipe sitting in the air. You put it in ground, you have that solid surface contact with it, and it sucks the heat off really quick. So we don't insulate those, and we have no lag in the water cooling off. It cools off almost immediately when you shut off the hot water. So every time you turn on the tap, you have to flush the whole line to get that through. The code doesn't allow that without the amendment in Utah. And we have a bunch of other stuff in here that doesn't allow it. In fact, in a commercial job, you have to insulate the hot water line all the time, everywhere, for the most part. You don't have to insulate strainers and control valves and stuff like that if they're less than an inch in diameter. And direct buried piping for fluids that's less than 60 degrees for the reasons we just talked about. But here's one that's been in the code, but it's been clarified here. In radiant heating systems, sections of piping intended by design to radiate heat. And that's a typo. It's intended by design to not radiate heat. So what this is saying, we have a radiant heat system, and we have all this piping running all over to manifolds, and then we have manifolds, and then we have the pipe in the lightweight concrete floor, or we have it in the slab underneath. What about all the piping in the mechanical room? Should that be insulated? The code has said it forever, and we just haven't enforced it. You go into a home, you go into a boiler room in a commercial building, and if it's a small commercial building, you won't see it insulated. You go into a bigger commercial building, the engineer expected it to be insulated. How hot is the pipe running? What's the temperature of the water in the pipe in a boiler system? It's going to be around 100 to 120 degrees on the radiant portion. What's it going to be on that pipe going to the hot water tank where they're making the hot water with the heat exchanger in the tank? It's 180 degrees. What does it run into radiators? And when you're using air handlers with hot water coils to them, you're running 180 degree water to them. So we have 180 degree water, and we have a big temperature difference, don't we? And so we're wasting a bunch of heat going where it's not supposed to go. So with a radiant system, the code has said, and it's clarified a little bit better, the piping going to the radiator, whether it's a floor or an actual baseboard radiator, it needs to be insulated to the point, and then we don't insulate, of course, where we want to radiate the heat out. If you do baseboard hot water radiators, just that look like an electric one, but they just have hot water run, 180 degree water, that's what you run through them. So the only portion we don't insulate is that's doing the radiating. We don't want to be radiating it everywhere. I'm going to throw in here, I didn't put the slide in, but if we have that recirc loop on that commercial building that we're circulating hot water around and then serving all the bathrooms, of course that's been insulated. It's been insulated forever. If you're doing it in a single-family dwelling, it's supposed to be insulated, and we never insulate that. We almost always miss that. So here's the other half of the one we talked about before, the operable opening interlocking controls. And so they go a little bit further. They do say set the cooling up to 90, set the heating down to 55, and then the controls should be configured to shut the system off entirely when the outdoor temperatures are below 90 and above 55. So if it's a mild day outside, just shut the system down. Don't set it up or set it down. Just shut the system down. Refrigeration equipment performance. This is, they've eliminated some duplication in there. And basically, we have some federal requirements now for refrigeration in our grocery stores, in our refrigerated warehouses and everything. And this is one, I have a note here, ensure it's on equipment schedules. And unfortunately, we don't have, maybe we have a mechanical engineer listening or an architect listening. Unfortunately, I've seen too often we have mechanical schedules and it has everything that the HVAC ME wanted to put in there, but then they have gas fireplaces and they have refrigeration equipment that's provided by someone else, and we have all these other, quote, these other mechanical systems that aren't included on the equipment schedules. We need to identify this stuff on the plans. We need to make sure that it's on there, whether it's a separate sheet. A good example is commercial kitchens. They're usually designed by Captive Air or something like that, not the ME on the job. And so they're not on his mechanical or her mechanical pages, but there needs to be a page in there for the commercial kitchens. Again, it's just making sure that everybody's communicating. I have to share this one. I shared it the other day when we did the makeup air class. If the ME on the building isn't communicating with the ME that did the commercial kitchen, we can end up with the problem I had at a grocery store up here. It wasn't a problem for me, it was a waste of money for them, that I put in a makeup air unit for the big deli that they added to a grocery store, and this is back in the 90s. It was designed by an engineer. I just bid and installed per the engineer, and it was like a 3 million BTU direct-fired Resner makeup air unit. We did the job. I went out there to do the startup and do the commissioning on the unit, and I couldn't get the unit to fire. It wouldn't fire. And the problem was the grocery store, with all of its rooftop units, were bringing in ventilation air through each rooftop unit. So you have a grocery store, it has 8 or 10 or 12 rooftop units. Each one of them's bringing in a little bit of fresh air. Well, you turn on these two 20-foot hoods and are exhausting 6,000 or 8,000 CFM, and guess what? You're bringing enough air in already. You didn't need a makeup air unit. The makeup air unit had differential pressure controls on it, so it would sense when the building was going negative, and then it would just provide the right amount of air for whatever you were exhausting. Well, you already had plenty of air, and you didn't need it at all. Kind of a waste, isn't it? I think it was $50,000 or $60,000 that I charged them for that system, and they didn't need it. That's where all the players weren't working as a team. And the code now addresses that and says that you need to look at all the air, ventilation air and everything in the building when you're providing makeup air. If you have more than 1 million BTUs of service hot water heating, and this is for the water, this isn't boiler, this is for the water, the minimum efficiency is increased to 92% from 90%. And that's not a big stretch. That's a pretty easy stretch to go there to get to that efficiency. Okay, this one relates to plumbing, more than it does mechanical, but it's in the service hot water heating. And this one needs to be discussed, and I don't know if any of you have worked around it, but if someone has been enforcing the heated water supply requirements that have been in the code now for 2 code cycles, this is the 3rd, we got kind of a problem. This was adopted, and I remember I was at the code hearings when this was being discussed, and what the problem is there's a guy named Gary Klein, and I can't remember what his company is, but he insists that we are wasting billions of gallons of water in public restrooms trying to get warm water to the sinks, right? And it's true. How often do you go to some place? In fact, I've flown quite a bit over the last 5 or 6 years, and it was completely refreshing to go into the new Salt Lake Airport and wash my hands in the restroom, and I had hot water. I had warm water, because almost never do you get warm water when you're in public restrooms. And the reason is the way it's piped. So anyway, Gary put together this code change, and it took him 2 or 3 code cycles to get it through, and everybody was fighting him on it and everything. And he created some tables that gave you the approximate internal volume of the inside in ounces of water. So if you had a foot of 1/4-inch tubing, or excuse me, 3/8, I don't have quarter on this table. If you had a foot of 3/8 type M copper, you have 1.06 ounces in 1 foot of pipe. And he came up with all these charts, and they're in the code, and you look at it and you go, I don't know what the hell he's talking about. Why are we even going down this road? But here's the bottom line. And then we have a few code sections that talk about it in this that he created. For piping from the nearest source of heated water, from the water heater or from the recirc loop or traced heat loop to the fixture requires either a maximum pipe length or a maximum pipe volume. So what he's basically saying is we want that lav, that sink, to be close enough to the source of water, and that could either be that 2-inch pipe running around the building that's insulated from where it connects to that, or the undercounter water heater. We want to limit how much water you have to clear through the tube before you get hot water. I mean, it's pretty logical when you think about it. And then from the tables he included, the flow rate through 1/4-inch pipe should be less than 0.5 gallons per hour. Flow rate through 5/16 less than 1, and 3/8 less than 1.5. The intent again is to reduce wasting previously heated water that is cooled in the pipes that don't require insulation. So let me pull this together with a diagram I made, and this will help make it. So here's a public restroom with seven sinks. And here we have our 2-inch pipe running up above the top there. And at A, it connects, a little branch goes down. It's a 1-inch branch that drops down and goes across, and then it reduces to 3/4, and we have these little 1/2-inch stubs. That's not unusual looking, is it? I mean, that's kind of what we would do. The large, darker line, the 2-inch line, is insulated. And so with this code requirement, we start measuring at A, and we figure out how much water we have to dump down the drain before we have warm water at our fixture. So that's one drawing. And then we have another drawing, option 2. And we've dropped our 2-inch down so it runs right behind the sinks, the lavs. Do you think plumbers want to do that? I hear chuckling out there. No. No, they don't. In fact, they're freaked out if they have to do that. I've been doing this for 50 years. Why would we ever want to change? Do you think you ever get warm water to a sink with that configuration?
Long time.
Long time. And we have a requirement on those public restroom faucets that they can only flow so much water. You're never going to get hot water to them. And so to add to the ridiculousness of the whole thing, we have a 200 and something thousand or 300,000 BTU water heater, 200-gallon tank, sitting down in a mechanical room someplace, right? With 2-inch copper pipe running all over, insulation, the cost of the pump to run all the time, and we're not getting any stupid hot water anyway. So we're spending thousands and thousands of dollars, and it doesn't work. Let's look at the calcs. So taking the tables and drawing the numbers here, you can look at this later. You got full-size ones on your email. But let me just, this is taken off my diagram. So the length from A to B is 10 feet. The length between each fixture branch is 2.5 feet. The length of each branch to the fixture is 1.5 feet. So we have the 1-inch pipe coming down, and we have 15 feet. And that's 1-inch pipe, 15 feet times 5 ounces per foot of pipe. We have 75 ounces of water in the 1-inch pipe. And I'm going to the furthest sink. 3/4 pipe we have, because it reduced as it went across that lower manifold. And we have 7.5 feet, 3 ounces in every foot. So we have 22.5 ounces in that line. And in the 1/2-inch line that's coming out to the sink, we have 6 ounces. So we have 103.5 fluid ounces. How many ounces in a gallon? 128. Good, Carl. So we almost have to clear a gallon of water. And what's the flow rate on that faucet? I think it's, or is it 0.5? I can't remember. But it's low. Yeah, I think on a public lab, it's way down there.
5.5.
Yeah, it's low. Are we ever going to clear it? 128. Were you looking at the board? I wasn't paying attention to it. So we have 0.81 gallons of water we got to clear to get hot water to that sink. I was testing you. Public metered lab is 0.25, and other than metered is 0.5. So considering the maximum flow rate of 0.5 and 0.81 gallons, it only takes 97 seconds to get hot water there. You imagine standing there for 97 seconds, waving your hand in front of that stupid thing, trying to get 0.8 of a gallon of water out of it.
So what are we supposed to do to these faucets?
Well, I'll tell you what I think you should do, and this is what my son's talking about.
2-inch loop.
Well, that's right. No. You put a little at-source water heater underneath the van and run a number 12 wire to it, and you make hot water as you need it. And you'd never consume as much energy, even though it's electric heat, as you would with that big 2-inch loop that's running through the whole building that doesn't give you hot water anyway.
Are you requiring a mixing valve on that little electric heater?
Are they requiring what?
A mixing valve? SSC 1070?
I don't think I think those heaters are,
They're not listed in SSC 1070s.
I read something someplace, or I listened to it in code hearings, that the temperature that they put out
It's lower.
is lower and they qualify.
Unnecessary.
Yeah, why do you need to mix? You're not putting out real hot water. You're putting out the water that you want, 105 or whatever it is. That's a good code change, I think. Now, no one wants to do that. I mean, that's kind of stupid, really, when you think about it. But at least you get hot water at your sinks, warm water at your sinks, right? Yeah, Gary he faithfully worked hard on that one to finally get it there. But I think it's a completely logical and a big savings. Jeremiah, my son, told me that they have buildings that they're just abandoning all that stuff now. As they upgrade their buildings, they just go in and they put in at-source water heaters and some of them they put in a little closet or something like that, and they just have it right there close, and it's so much simpler. Okay, so our credits on our mechanical side. Remember I said at the first, and we talked about this a little bit before, we need 10 credits from those tables, the 5 tables, and we're going to see some more of those. Based on the group of the building and credit calculations where the building contains multiple groups, this is important. Credit from each use group to be weighted by floor area of each group to determine the weighted average building credit. Credits from tables or calculations shall to be achieved where building comply with one or more of the following. So we have efficient HVAC, reduced lighting power, enhanced lighting controls, on-site supply renewable, and so on down. High efficiency service water heating, enhanced envelope performance, infiltration. How do you know you have reduced air infiltration? Your blower door testing, right? And so you meet it with less leakage. And again, where it's not required to have energy monitoring, you can do that, or fault detection and efficient kitchen equipment. New buildings need 10 credits. I don't need to reread that. And tenant spaces, TIs, need 5. And I'll tell you right now, in most cases, achieving all 10 points within the envelope is very, very difficult. And we need to do 3 sets of comm checks to show that we've done this. You need your envelope, you need your mechanical, and you need your lighting. And your lighting is actually 2 different reports. And as I mentioned, I should have circled this one. It's going to require cooperation, teamwork between different design professionals. There's just no other way to do it. Now, I had a fairly large comm check that I tried to put in and tried to get it to pass, and I might have mentioned this earlier. It's not an easy thing to get this to work, strictly trying to do it with the envelope. You know, you just can't make enough improvement on the envelope to get the full 10 points. Well, you can, but it's pretty tough. You'd have to go overboard on your windows maybe, and I think what you're going to see for design professionals to meet this is we're going to see more and more PV solar on roofs, because you get big bang, and sometimes it's big bang for your buck, because PVs come way down and you can offset quite a bit with PV. Now, I know it's not popular with everybody, but and I'm not going to get into debate of how environmentally friendly it is to manufacture panels or everything, but when we reduce the load at the building, it's where it can really make a difference. So again, these are the occupancy tables that we have in the code. And I'm going to jump to, we had that first example. You need to change brands. That doesn't fit like it used to.
If you said,
Shows how old I am. What?
if you said, go to blueberry instead of raspberry,
Yeah. Yeah, see, and
that doesn't work.
that doesn't work either. So additional efficiency, again, for Group B. And we glanced at this a little earlier. And if we look at at this one, the bottom one, the envelope, the UA of the envelope, you can see that it's maybe you can get away with it in 5A to get 10 points, and maybe you can in 6, which makes sense because they're cold climates. Let's look at a different one, a different table. This one is the same table, but I highlighted those that are related to the mechanical that we're talking about. And again, this is to help us understand how these tables are written. Heating efficiency improvement, again, it doesn't do any good. In fact, heating efficiency improvement all the way across doesn't even start giving you any points until you get up to 5A, and then there's just a little bit, and it doesn't even give you anything here. Cooling efficiency improvement, you get points all the way across. 10% heating improvement, you get a little bit more as you get across to our climate zone. And cooling, you get a little bit more. So I think as you look at that, you can see that you might have to do, like in our climate, we might want to do some heating, bump it up to 10% on heating and bump it up.
Right.
Yeah.
Is our standard 80% efficient, or what's our standard? We're saying 5 or 10%?
Our standard is 80%.
80.
Yeah, our standard is 80%. And so you can, and that's a good point you bring up, Chris. So we can pick up a point or two, depending on which climate zone, and then we can pick up a little bit in cooling too, right? So between upgrading our HVAC, we can get 3, 4, 5, 6 points, depending on what our climate zone is and such. And then we'd need to look someplace else. We could enhance our lighting controls. We could, a big one, reduce lighting power. What is reduced lighting power? We have, and it was kind of a bonus for a number of years until the code caught up. We have lighting power allowances, and they're based on lighting power density, so many watts per square foot. And we have all these different uses in buildings, all these different groups, and we assign a lighting power allowance to all these different uses. You know, in a classroom, we need a little bit more light than we need in a warehouse. We have all these different things. And when these tables first came out, LED was just coming online, and they were based on what was available. You know, CFL was coming on and stuff like that. Well, all of a sudden, these became more available, and I was getting people sending me lighting comm checks, that said, pass by 67%. And it's because our code was 6 years behind, and they were putting all these great LED lights in there that are 80% more efficient than what they were in before. And so we had these huge savings, and they could get away with anything in a building because the lighting power, they passed, you know, so much if you did a performance or something like that. And even down here, if we look at it, I have to put my glasses on. Climate Zone 5B. If you reduce your lighting power enough, you get 8 points. Digital controls, you can get 2 points. On-site renewable, look at that, you're almost there with your on-site renewable. And so we have a lot of options to get to 10, but you're not going to get much trying to just do it with your envelope in most cases. You do in the A climate zones simply because if you enhance the envelope and you reduce the infiltration in those zones, we don't have to deal with all the humidity and everything. And so you have some pretty big savings there. Let's go to the next one. Try to see if there's anything else I wanted to. Heat pump water heater, nothing. All the way across. Fossil fuel water heater, nothing, all the way across. Renewable water heating, nothing, all the way across. Why? Again, a B occupancy doesn't use any water. R's and I's. Now let's look at R and I, so that's residential and institutional. Everything from prisons to halfway houses to, care centers, large care centers. Recover or renewable water heating. 10, 9, 11, huge. Climate zone 5B, 14 points. What would we call recovered water heating? Renewable, we know that's using a renewable source that we defined earlier. What would be recovered?
Recirc.
Kind of. We have this building that has a big cooling load on it. We're always cooling, and what are we doing? We're throwing heat away. We can recover a lot of heat from it. We have what we call de-superheaters and stuff. You can even put them on your home air conditioner where you can heat some of your hot water off your waste heat. But in a building, a big building that we're cooling all the time in the middle or whatever, if we can recover from whatever we're wasting, whatever we're throwing away, if we can recover some of that heat and use it to make our hot water in a use or occupancy that needs a lot of hot water. So we're in a R and an I, we use a lot of hot water. You have a 500-unit apartment project going up everywhere all over the place. Can you imagine how much hot water those places use first thing in the morning when everybody's getting up and showering? Reduced air infiltration in climate 6A gets 13 points. Why would 6A give you 13 points? Where's 6A? I'm not going to go all the way back to the table. A is moist, so A is moist, B is dry, and C is marine, which is basically the coast of California and Oregon and Washington. It's not near as humid, but it still has some humidity and it's marine. So what would 6A be? Alaska's 7. All right. It's going to be Maine and Rhode Island and what do they have up there?
Maple syrup.
Maple syrup.
He's from Vermont, so.
But what do you have? And thinking about reduced air infiltration. If we reduce our air infiltration, we have a cold environment, right? And what do we have in the summertime? Humidity. So if we don't have to deal with the humidity all summer long, because we reduce our air infiltration, we don't have all that moist air leaking in, and if we can address how dang cold it is, I think Chicago might be 6A. They're on Lake Michigan. Those are nasty places to be in the wintertime, aren't they? You're still cold thinking about it, aren't you? Got your coat and your hat on, just from the memories. So the tables actually make some sense when you look at it. You get points where you're going to save. And so, again, it's going to require the whole design team to get together and say, okay, here's our building. We're in climate zone 5B. where can we do this? And some of it you can do pretty inexpensively, but you're gonna have to mix and match, and you're gonna have to take some on maybe the envelope, some on maybe the lighting, some on maybe the HVAC, so you get your 10 points. And they're going to have to do it together because since it's a web-based comm check, you're going to have to do it all on one comm check. You can't have the ME's comm check and the illumination guy's comm check and the envelope guy's comm check all separately. They're going to have to all work together because that's how you generate the report. You can't get a passing report unless you're looking at the full integrated building. I think it's actually a good thing. We need to have that better communication. Please.
Do you ever worry about a signature on a comm check?
Do I worry about signatures on comm checks? I don't know if you're going to like my answer, but I worry about them on every comm check and every res check.
Why?
And my comment that I write up is the person that is certifying this is accurate needs to sign the comm check or the res check. I'm laying it in their lap that you are responsible for that document. He has certified it. You know, I've seen so many of them that they just throw crap at it. I almost said another word because it's, what are they throwing at? I mean, they have put so many of them sit down and they start doing that comm check or that res check and they go, oh, I'm within 2%, and they just start fudging and hitting stuff. I've had them turned in that I had a couple of them turned in that they had window U factors of 0.05. Now, what would be a window with a 0.05 U factor? That's an R20 window. Does anybody know how to make an R20 window? If you do, come see me. I'll find someone with some money, and we're going to start a window company, and
No glass.
we're going to be billionaires. If you could make an, you know, the guy didn't know what he was looking at, and he just started throwing crap on it. So I want them to think about that they're signing a document that says this is accurate. Now, maybe some people don't care, but I always word it to say, you know, I want to know who's certifying that this document is accurate. And they have to have some communication. They have to be talking to one another to get it right. Now, if you're not enforcing, for everybody out there that isn't enforcing the code at all, the first step would be get a comm check turned in or get a res check turned in. And let's kind of look at it and see if it's passing, and maybe there's a couple of things you could look at. But they're really pretty easy to review once you've got familiar with it, because you just look for stupid stuff that doesn't make sense, like the 0.05 or someone that has a high pass rate. You know, the lighting ones that pass by a bunch, you know, that would be a red flag until you see, well, it's lighting and it was a 2018 or a 2015 comm check. But yeah, that's my opinion. You know, if you don't want to ask for it, Chris, I'm not going to tell the whole world that Chris Whites isn't asking for signatures on his certificates. Only those that are listening right now. But you know, it's not a huge deal, but there's always something else I'm asking for anyway, so that they can sign it. And you know, I would love, and occasionally, I love to do a review when they've paid attention to what we called the last time and they actually implemented on the plan so that you can move right through your plan review. It's kind of a unique concept, isn't it? Commissioning. What is commissioning? Commissioning is when the building is all finished and there's several pages in the back of the IECC, the end of chapter 4, that go through what needs to happen to ensure everything's working correctly. And engineers have been doing it for years and years and years. If they have a big building that they design, they have responsibility and liability for the building design. And I've done many jobs that I had to have them commissioned over the years because it was an engineered plan, and the engineer was trying to CYA, cover his butt, because he didn't want to be held responsible for someone that installed it incorrectly. And so you have a large building that goes up, the engineer requires commissioning, he writes up a plan, and then the building is set up correctly. That's stuff I talked about right at the very first with the Energy Star. What they are doing is their program is maintaining the commissioning. So you get a building all set up, and then you get a couple of building engineers in, guys that are glorified maintenance guys that don't know what's going on, and they start changing set points and changing this and changing that, and you have a building that's wasting tens of thousands of dollars because it's not balanced correctly, it's not set up correctly, it's out of commission. And recommissioning is a big thing. Coming in and you go into a building, you hire engineers to come out and recommission your building, and everybody's patting each other on the back because they're saving $12,000 a month because they recommissioned the building. Well, how about you commission it the first and then you maintain it in that state all along? And that's what the code's trying to head to with diagnostics and everything else. And that's what Energy Star for commercial buildings does, is it pushes you to maintain those. So the code, 2 or 3 code cycles ago said, you know what, we're not gonna just rely on engineers because, you know, we have this 2 dirty words that come out right now. You ever heard of value engineering? What's value engineering? The number's too high, so let's see, mechanical, weren't we talking about this at lunchtime? Let's cut out mechanical, let's cut out this, let's cut out this stuff. I just finished a case that went on for a couple of years, 4 years it went on. And the whole thing was ridiculous because they value engineered this really nice apartment project and they screwed it up. I mean, completely screwed it up. And they were having so many problems. They were having hot water lines to coils, heating coils burst. And when one bursts, and it's the old value engineered, what you'd use for a heat source. Piece of crap water heater, 60-something% efficient water heater, which they should never be able to use because it's not efficient enough. And an air handler that has a DX coil and a hot water coil. And if the DX coil freezes, it doesn't hurt anything. Your air conditioner freezes, that doesn't hurt anything. But what if it's this far away from the hot water coil? And it freezes the hot water coil. And what's the pressure on the coil? It's not 12 psi like a standard boiler. What's the pressure? It's building pressure. So what happens? You freeze the hot water coil. As long as it's frozen, nothing happens, but as soon as it starts to unthaw, we end up hot water coming from the water heater and spraying all over. And every time it happens, it's $50,000 to $80,000 damage. And it happens time after time after time because why? Because you value engineered the quality out of the system. I don't have an opinion on that, do I? And I should be thanking them because I get paid to tell them what they did wrong. So commissioning. You can't value engineer the commissioning out if you have 40 tons of cooling capacity and 600,000 BTUs of combined surface water heating and space heating capacity. That's been in the code for a while. So once your building has that, you need to commission your building. And there is a complete set of requirements in the energy code that tells you what has to be submitted with the plans, which includes a commissioning plan. The commissioning plan needs to be part of that. And then as you get to the end of the building, your building is never fully commissioned at occupancy, at final. But you can do a majority of it, and then as the building is brought into operation, they're starting to use the building, that's when the commissioning is finished. And it might take 4 months, it might take 6 months to fully get that building commissioned, because why? Because we have to go to different seasons and we have to adjust everything. But it's a huge savings. Just a massive savings, and that's why it's in the code. This is in here for information purposes. There's no code change on it. It stays exactly the way it's written, but it would be really good if, we got the word out there and we started requiring it.
So Brent, can you repeat what commissioning is?
Okay, the question is, what is commissioning? Basically, it is you're testing airflow, you're testing water flows, you're testing temperatures, you're testing balancing of all the registers, you're testing the control systems.
Who is?
Good question. Typically what happens, and in fact, I've been around several of them. My son was involved in a couple of them up there at that property at the mouth of Big Cottonwood Canyon, and I went up a couple of times when I was there. And the project was designed by Colvin Engineering and Van Born and Frank. These are two of the leading mechanical engineering firms in the state. Van Born and Frank had an engineer up there assisting with the commissioning. And so one firm does the design and another firm does the commissioning. Third party engineers. They have to have engineers, and then of course you have the subs that might be involved in there doing some of this stuff, but it's directed by a third party engineer. And they work. I mean, they really do, and they find a lot of problems. I'm gonna brag. I'm not gonna brag about my son in California, I'll brag about my son that's here. I can brag about them both, but anyway, he worked with me in HVAC, and then for various reasons, he left the HVAC industry and did something else for a number of years, and then decided he wanted to get back into it, and he started working in commercial buildings. And he started out just doing maintenance, changing filters and doing basic stuff, and then as he became more and more familiar with the controls and stuff, he's pretty sharp with those, he started bringing these buildings back into commission just based on his knowledge and experience. And so what do the building owners notice? With these reports that you put out, well, why are we saving $5,000 a month on our utilities? And it's because he's just putting the building back where it needed to be. So I've been around a lot of them, and I've been around, as he's moved from new building to new building, and watched and watched him do the commissioning and talked to him, about it, because, we have similar likes and everything, and so my wife thinks it's nuts that we can sit there and gab on the phone for an hour about building HVAC, but I don't say anything about what she can gab for an hour about, but
Don't criticize her.
I'm not. It's okay. But anyway, it's putting the building back the way it was designed. And so in fact, if you go to the IECC there's quite a few specifications in there and what goes into it. But it's good experienced mechanical engineering firms, the higher end firms, they all are very, very familiar with it because they've been doing it forever. That's been part of their plan forever. And it just makes a huge difference. I mean, it's just multiplied by 100. If you have your home system and you keep the condenser clean, you keep your filter clean, you keep your coil clean, your duct work is clean, your registers aren't blocked off, and all these different things, you're more efficient. Well, you multiply that by many times, and that's what happens on a big building. And when it's off, you can waste so much energy. You waste huge amounts of energy. Lighting. And we're going to go through this a little bit quicker, I think, because it's actually pretty straightforward, and it's something that you're going to have to spend a little time in the code. thing about lighting requirements, they have so many triggers. When you get to this size of building, you trigger this, and when you get that size of building. And so you have all these different triggers that I can't identify every one of them in these, but there's a few things that we'll touch on real quick. High efficacy lamps. By definition, it's a compact fluorescent or LED or T8 or smaller diameter linear fluorescent lamp or other lamps with efficacy not less than 65 lumens per watt. So I think we've become familiar with lumens as we're buying light bulbs. You know, a 100-watt light bulb, I can't remember how many lumens it was, but we buy a 13 or 15 or whatever watt LED light bulb and we get the same amount of lumens. That's the measure of the light. And so it just depends on the bulb and the fixture. Sleeping units. Here's a new requirement in the code, blue text. A minimum 90% of the lamps in permanently installed lighting fixtures serving dwelling units, excluding kitchen appliances, kitchen appliance lighting to be provided by lamps with efficacies of not less than 65 lumens per watt or luminaires with efficiency not less than 45 and so on. I don't need to read through it all. And then it needs to comply with 405.24, 405.3, which is daylighting controls and lighting power allowance tables. And so what that's really telling us is we have these limits on how, minimum efficiencies, but then it tells you still have to comply with your daylighting controls and lighting power allowance tables. And so we have multiple pieces that, again, we're trying to fit through. So what are the controls that we see? And I don't know how many of you have spent some time in here. I'm going to guess that most of you have not spent a lot of time in it because it's pretty darn confusing, and I don't think that we push very hard on it. We get in the big buildings, they're doing it because they know they want the buildings to perform. But in our smaller buildings, we haven't pushed too hard. And I'll be honest with you, sometimes I don't know if there's real value in pushing too hard on it. I mean, how much are we going to save if we shut those lights off? And maybe I'm speaking out of turn, or I shouldn't be saying that, but what's our return on investment for some of this stuff in a small building? What do? You will see that we have a daylight zone that comes off of each one of these windows. And we'll have a table that comes, well, we'll show you here in a minute. But we come in so far where we're receiving the benefit. But we got 7 or 8 feet between the two windows, right? So we don't have a daylight zone right underneath that monitor coming out. And so the code still hasn't caught up with the dead spaces between windows, and sometimes the windows aren't very tall. They're shorter, and so we don't get a lot of light through. But until we learn, what's in the code and we can see where we need to apply it, I guess we can't apply it. So anyway, here are the general lighting controls that we have identified in the code. Occupancy sensor controls. What's an occupancy sensor? You walk in the room and it turns on the lights, right? Anybody who have one in their house? I put one where you walk out into my garage. And I did it because of my grandkids. Because what's just outside the door when I walk out of my house into the garage? There's a second fridge. What's in the second fridge? Soda, ice cream, all that kind of stuff. So the grandkids come over, and guess what? Grandma and Grandpa never say no. Do we? It's payback, right? It's payback. I raised their parents. So they go out and they turn on the light, get whatever they want, and come back in, and it's You walk out and the light's on, and it's just the light's on almost all the time. So you step out of the door now, and I have a little occupancy sensor and just a single light right there above the fridge. You walk out, turns on the light. 2 minutes later, when no motion sensed, the light turns off. The 2021 code has a whole bunch of stuff in it, residentially, for occupancy sensors in houses. And that was part of the heartburn, I think, why we didn't adopt the 21 code. I have mixed emotions. If they want to take some of it out, I guess that's okay. You know, I'd rather have a lot of the other stuff in the code. And maybe there's a few places in here that it doesn't belong, but I think generally, my experience at the county, when I was working at the county, for a few years, they actually let me have a private office. Remember that, Kirk, when I was down around the corner? It was so nice. And then they stuck me in a cubicle after that.
Pepto-Bismol ones,
I don't know what it,
the pink colored ones.
is it pink?
Yeah.
That one around right next to the back door. It was great. But I had an occupancy sensor in there. And I would leave thinking, oh, I'm going to be right back in a minute. And so I wouldn't turn before I had it, I wouldn't turn my light off. And then you get to the counter and someone grabs you and 4 hours later you get back to your office and the light's been on the whole time. And so I think there's a real place for them. So in our smaller buildings, you can just about meet most of the lighting control requirements with occupancy sensors. We have some time switch controls, and these typically are going towards bigger buildings where, the building, everybody goes home at 5 o'clock. Everything shuts down. We shut down all the lights, we leave, the stairway lights and stuff. Daylight responsive controls, what are those? Those are the ones that the sun's coming through there, we shut off the lights that are in that daylight zone. And then we have specific application controls. But generally, they tighten up things. And they do save some money. So occupancy sensors right now, everything in black is where occupancy sensors are required right now in the 18 code, and corridors were added in the 21 code. So all these areas have occupancy sensors. Do you have a problem with an occupancy sensor in a restroom? Is that a big deal? You walk in, the light turns on. It's not a big deal. Most of these aren't. I'll admit that when I was in that coveted office down there, every so often, if I was really involved in something, I might have to wave my hand to turn the lights back on. But for the most part, these are good places because lights get left on everywhere. So in some places, some of these aren't allowed to be controlled. They're set and you can't do anything to them. Some of them you can allow them to be shut off or manually switched. But anyway, exemption full auto on controls allowed in public corridors, stairways, restrooms, and stuff like that. So those are ones that are just completely auto. They don't have switches that will allow you to override. They're basically areas that could endanger someone. I mean, I went to high school, and I remember, your buddy's in the restroom, and what do you do on the way out? Turn the light out on him, right? No one else had ever done anything like that, have you? Carl has, because he started laughing immediately. With occupancy sensors, and there's no problem with them staying on for 5 minutes or whatever. There's a lot of other functions. Automatically turns on the light turns the light off within 20 minutes of leaving the space, either manual on or automatically controlled to turn lights on to no more than 50% power. Incorporate a manual control to allow occupants to turn off the lights. And the exemptions, again, are these that you can't manually turn them off. Warehouses, that can be pretty dramatic if you don't have motion in an area, if you don't have an occupant in there. In 20 minutes, you drop to 50%. And at the end of the day, they're turned off by a time control. You don't have to walk through the whole building and turn them off. I remember one of the first code hearings I went to. Has anybody, any of you other, have you ever been to one, Chris?
No way.
No?
I get enough sleep in my own bed.
Kirk, have you ever been to one?
Yeah.
They're kind of interesting, and maybe I'm sick because I've been to so many of them. But one of the first ones I went to was in Charlotte, and I still remember getting to my hotel, and it was later, it's like 10 o'clock at night or something. I look out, and there's a big building that's right beside it that's 20-something stories. And guess what? Half the lights were on in the building. All over the place there's lights on. And there weren't janitors or anything in there. They were just on. And I was there for like 7 or 8 days, and every time you'd look out at night, it was the same lights that were left on. How much energy waste goes on across the country?
That was emergency lighting.
I'm sorry?
That was emergency lighting.
Emergency lighting. It was kind of ridiculous. They need to uniformly reduce lighting power to not more than 50% of full power within 20 minutes of the occupant leaving the space. So in this case, you can leave the lights in the warehouse on at 50% or less, but you don't have to shut them completely off. And this one, corridors, exception, corridors with less than 2-foot candles of illumination on the floor at the darkest point. What this is saying is you might have a corridor that is not well lit in the first place. If you have a poorly lit corridor that only has 2-foot candles in the darkest spot, we aren't wasting a lot because we have minimal light in there anyway, so we don't need to reduce those. That make sense? Each area building that is not provided with an occupant sensor control must have a time switch control to turn lights off automatically. So the occupant sensors will take care of a lot of stuff, and in our small buildings, we don't have to do anything but put in the occupant sensors. We don't need a timer that shuts down everything when we know the building's empty. And then we have some exceptions there, where you have to have light for a specific application, for instance, or patient care, where it's going to create an occupant safety or security issue, and lights that's intended for continuous operation. I am not opposed to lighting for security. I live in a good neighborhood, but I still have lights on at night.
Street lights.
Well, I leave my porch light on in my, but how do I control it? I do control it in a method that really would comply with the code, and it's an astronomical timer. What's an astronomical timer? It adjusts the time on and off every day. You just program in what the date when you install it, and it adjusts for the changes in sunset and sunrise every day. And they used to be horribly expensive. You'd have to pay for these big expensive things. This is just a little Leviton thing that fits in the place of a regular light switch. And you just program it there on it, and they're pretty slick. I guess I could have it drop in volume, but yeah. or brightness, but with LED lights, they're not big lights, and I just like the security of having it on. Beside that, if it's dark and the pizza guy's coming, I don't have to worry about turning on the lights so he can find my house. Time switch. So we talked occupant sensor, now we're talking time switch functions. And again, there's requirements, there's exceptions, but generally, commercial building needs to have a time switch control that automatically turns off the lights when the space is scheduled to be unoccupied. And it has a bunch of other stuff in there. Lighting reduction controls. Now we're going to talk about reducing the lighting. And the first part is allowing the occupant to reduce the lighting. Now, Carl has come and recorded. How many times do you think you've recorded or filmed me? 20, 30 times, somewhere in there. And he's probably heard me most of the time complain that I couldn't shut the lights off right across here. In fact, I celebrated earlier today when I came in. These lights right here were on, and I was able to shut them off. Why? Because I want you to be able to see my slides. Well, what this is saying is occupants need to be able to reduce their lighting. You know, there's my office at home, I have a dimmer because sometimes when I'm just all on my monitors, it's nice to have it a little dimmer, and I want it, but when I'm reading or something like that, I want it a little bit brighter. So you need the ability to reduce your light as the occupant would like it by not less than 50%. In a reasonably uniform pattern with intermediate steps in addition to full on and off, or with continuous dimming. I want to write a code change that says if you have a classroom setting that you need to have the ability to shut off the lights at the screen. You put photographs in there, and I don't have any in here, I don't think that required it, but oftentimes, well, if I had bright light, you wouldn't be able to see this one. There's a lot of photographs you can't see if you have a real bright light. Reduction options, continuous dimming, switching to reduce not less than 30%, not more than 70% of full power, switching alternate luminaires or alternate rows of luminaires to achieve reduced output, which means you turn off every other light or whatever. Okay, well, now we're going to go into our daylight. And I'll spend as much time as you want here, but I think as we're approaching 3 o'clock, I know what it's like to sit out there for that long, and so I'm gonna move through these and stop me if you have some questions. So here are our rules, and this has been updated. Our 21 code has what we call a secondary side lit zone. So in diagram A there on the upper left, that section view, we have primary side lit zone and our secondary side lit zone. These are out of the commentary. Actually, they're out of the code. And they screwed up the diagram, I think, because they show the height is all the way to the corner where it should just be the width of the window. But anyway, you can see what we have is the primary zone is so far in, and then the secondary zone goes, again, that same distance. So what's the difference? Obviously, the primary zone is going to get more benefit from the outside light, and the secondary is going to get less. And so theoretically, they want you to do switching, independent switching in both of those. Then we look at the other diagram, B, and this is what I was talking about a little bit, and this kind of fits this room, other than the full height wall. We have our window And I really think the H is the height of the room, not the, I think they've misdrawn that diagram. But you see on this one, we have a wall in between. Now, how do we deal with that? You can't see that, can you? How do you deal with that little strip that exists right here in the middle that's not in the daylight zone? I don't think the code's addressed that yet. Not completely. Because it generally is 2 feet on either side. So we got at least 7 feet, I think, right back there. And so we have 3 or 4 feet in between that's in a dark zone. So some of the things that the controls are supposed to do, and they've added that lights in primary side lit daylight zones to be controlled independently of those in the secondary side lit daylight zone. So that's exactly what I was talking about. If we go back here, the lights in the first primary zone need to be controlled independently of those in the second. To be honest with you, there's some other things in the energy code that we need to be worrying about before we worry about that in this room. But there are places that it becomes really important. The next one they added was dim lights continuous from full to 50% of full light output. And controls configured to completely shut off all controlled lights. So all of these have come about and they've been added to the code because of dimming now. When we first started doing this, LED was not the king of the lighting world. LEDs everywhere, all the big buildings are all done with LED now. And because we have LED, we can easily dim, and it's so much easier than doing a bunch of switching. They can order sensors on the fixtures. It's really simple, and if you have a larger building with a BMS, a building management system, this can all just be programmed at the computer, so it takes place. But that's what the code is looking for now. And then we have some wattage things. I don't think we need to read through that. You kind of understand it. So what's the next one? Before I open that slide, let me jump back in case you haven't read it. What is a monitor when we talk about daylight? Did you look at the slide quick enough before I went back? Now you know what a monitor is. Maybe you did already. And we have that in some buildings, don't we? It's not a skylight necessarily. It's a vertical piece of glass that we have some light coming through. And we might have a whole thing across a building, and it might be closer to the edge of the building, but we call them rooftop monitors. And they have here we have the ceiling height, and I almost have to put my glasses on. We have ceiling height, and then we have height all the way up to the bottom of the window in the monitor. And we want to use H, which is the height basically from the floor up to the bottom of the window in the monitor. And that's the width going back. We don't count any of the light that might kind of spill to our right, but because of the direction of the light's coming, that zone should extend back to your left the same distance as the height from the floor to the bottom of that window. And of course, if we have obstructions, then of course those are going to impact it. So these diagrams, if you read the code, like if you were to read this without a drawing and read through that whole thing, and I'm not going to read it out to you, but try to read that and try to figure out what the hell they're talking about without the diagram. So I think this is great that they put the diagram in so you can figure it out. And we just talked about that. And then we have what we call a sloped roof monitor, and it's the same type of thing. You're still going to get the light there. And we'll move forward from that one. Top lit daylight zone. It's a skylight. And because it's horizontal and it's not, it's not a vertical window that only lets light come in one way, you notice that we go 70% of ceiling height each direction for our daylight zone. And again, if we have some type of obstruction, if it's 70% of the ceiling height, then we consider it blocking completely. If it's shorter, like what? Cubicles, then the daylight zone could extend beyond the cubicle. Multi-story atriums, and we have the same type of thing where we we look at ceiling heights and we can determine how far, 70% of the top, but as soon as we have that floor come over, we're just counting straight down, even though you're going to get some light bleeding over. Daylight zones in atrium spaces, that's what I just showed you before I showed you the text. Projection factor. What's a projection factor? A projection factor is on the outside of the building. We have a window on the outside of the building. A projection factor is if we have an overhang on the roof that gives us some shading. We put them in for cooling, right? Well, they also are going to impact the light that comes through, and so we could have to make an adjustment on that because of projection factors. This is one on the roof monitors that we already looked at, the 70%. We don't need to spend any more time on that. Okay, specific application controls. And we are coming close. As we get to the end, in fact, Jacqueline, if I can hand you evaluation. She's going to pass out an evaluation. You don't have to put your name on it. You can be as blunt as you want to. I want to know what you would like to see. If you would like me to spend more time on this or that, just jot a note at the bottom. I want to provide you, with some value. Sometimes the part of it's kind of boring, and I apologize for that, but that's what the code says. So here's some of the specific application controls that we don't apply those to. And I didn't look up some of these code sections, but basically display lighting and task lighting and equipment sales lighting, there are times that we just need the lights to stay on and we're not going to worry about dimming those down. Task lighting for medical and dental procedures purposes, provide them with manual control. Lighting setback. And this is for our outside lighting. The IECC has now included a requirement that we start reducing light at least 50% after 15 minutes. So we don't turn it off, and we don't have more than 1,500 watts controlled together. 1,500 watts used to not be very much power. Remember, you put 3 500-watt lights on the outside of your house, you're 1,500 watts. But nowadays, 1,500 watts of LED is a lot of light. I have on the back of my house, I have 150 watts, and everybody accuses me of trying to put a sports arena in my backyard because it really lights it up nice. Especially my neighbor right behind me. Parking garage lighting controls. There's a bunch of new requirements in here, and some of these are really good, and the code has recognized that some of the areas that we really need to be addressing. And these also are dimming lights down when we don't need them. You know, I park at one of the off-site parking structures out at the airport, and they have all these lights up there. It's not a brand new structure, and they're on all the time. You know, when you're in the covered parking, and I just think, well, this is the stupidest thing in the world. And really, they're supposed to reduce it, and they're supposed to be looking at at reducing that light, and when you don't need it, to shut it off. They've recognized daylight transition zones at entrances and exits. What's a daylight transition zone? You go downtown, and when I go to see my son, there's a parking terrace where he lives, a parking garage. And you pull in, and if it's really bright and sunny, what happens? Especially when you're 70 years old. You pull in, and it is like pitch dark because your eyes are used to the bright. And so he's even mentioned how they've had projects and buildings that they manage that they've added daylight transition zones because they've actually had accidents, people pulling in, and they don't see the car that's coming to leave because you can't see anything for the first few seconds until your eyes starting to adjust. And so they should be separately controlled. And then we have some lighting reduction in response to daylight by at least 50% in areas around the openings. And so it's just common sense stuff. We'd like to have the security, we'd like to be able to see in there, but we don't need it on all the time when there aren't people in there. And we have a whole list that you can hardly even read, but these are all the places that are exempt from our lighting power density calculations. We talked about this a little bit earlier. When we are doing a calculation on what we are allowed for wattage in a particular spot, all these things can be left out. And when you notice that number 4 gaming casinos, they definitely have some lobbyists that are there with the code process, don't they? They got to have that. Antimicrobial lighting used for the sole purpose of disinfecting space. That kind of has become a big thing. This was actually put in the code before. It was written in the code, written or passed through the code process before we dealt with COVID. So this is the last thing that we really are going to be touching on here, and that's our interior lighting power allowances. We have 2 methods that we determine the lighting in the space, and guess what? Your CommCheck lighting certificate is based completely on this. They have to go through, they input all the lights, and they have a schedule on their plans of what their lights are. They just input each one onto the CommCheck, and you already have the square footage and everything from doing the envelope, and then the CommCheck will tell you if you pass or not. It's really pretty straightforward, but each light has to be entered, and if they have a whole bunch of different lights, it's going to be a long CommCheck. You know, that's just the way it is. And you can do it in 2 methods. First one is building area. You just kind of take the general use of the building and and you come up with the most common use of that building, like an office building. It's an office space, so you just have how many square feet. You don't do anything with restrooms. You don't do anything with lunchrooms. You don't do anything like that. But then there's a space-by-space method that sometimes you have to use it or sometimes it just works better, that you go to each specific space, and some of it might be offices, and some of it will be copy room, and some of it will be, you know, conference room and stuff like that, and you get a different allowance for each one of those, and then you total them up and see if you comply. unfinished spaces was added in the space-by-space method. Lighting power allowance for them is total connected power for those spaces, or 0.2 watts per square foot, whichever is less. If you're only doing part of a building, you have to use space by space. Building with unfinished spaces, you have to use space by space, because you don't know on that building, that shell you build, exactly what the use is going to be. And so that's the way you do it. And so these are the two methods again. Building area, so the top diagram, and I think you can see a little bit in the color. The top one, we're calling it an office or whatever, or living space, I can't even read it. But it's all, we took all the square footage and we've assigned it that building area, the most, the primary use of that space. And then in the space by space, we're breaking it out to individual uses in each of those spaces. And then you sum it all up. And kind of nice about that is you can trade off. If you don't use all your allowance in one, you can use it in the other. And so here's what we are looking at. And we just have tables in there. Of course, they're a lot longer than this. And so the building area, it's an automotive facility. So the whole automotive facility, you have 0.75 watts per square foot allowed. Convention center, it's 0.64, courthouse, and so on. Dining, bar, lounge, leisure, 0.8. Cafeteria, a little bit less. Dining family, even a little bit less. Dormitory, and so on. So we have all these different allowances based on the, I guess, lighting engineers and everybody have come up with what you need. You could still get a lot of light with these allowances. These numbers, they're in blue. They are smaller numbers than in the 18 code. So they have rolled them back some more. Because why? Because we're getting more and more efficient light bulbs. And in the space by space method, you notice how it's broken down. To more distinct uses. A laundry washing area doesn't need as much as a food preparation area or whatever. And so this might be a little bit better in some cases and not in others. So with this, you do your lighting power calculation, and then the code is very generous, and this is not new, but I threw it in for information. There's no change, and some of you might have seen this. The code recognizes, just like they recognize the casino wants more light, that if you're selling, for instance, retail area 4, if you're selling china, jewelry, crystal, or whatever, you're allowed 1,000 watts plus the area times 1.87 watts. So you're actually allowed a bunch of extra power because of what you're trying to sell. They recognize that you need a lot of light for those things, and so they give you an extra allowance there. If you're selling furniture, clothes, cosmetics, and artwork, you're area 3, so you get 1.05 watts plus the 1,000 watts. And if you're selling vehicles, sporting goods, small electronics, you get the 45, and then everything that's not in 2, 3, or 4, you get 45 watts per square foot. So it's not crippling anybody. You can get plenty of light out of LED, and you can use extra light to highlight your goods. LED's great. I did, back in the Cottonwood Mall days, I did a lot of work in the Cottonwood Mall, and we'd do a clothes store, and they'd put all these track lights like they have in this picture, but they had whatever halide or metal halide or whatever in them, and I had to add a bunch to my load calculation, my cooling load, for all those stupid bright lights that they put in there. That's kind of gone away. You get a little bit of heat from from an LED, but not very much. Lighting for plant growth and maintenance. And I don't know how many in here are real scientific, and maybe you can explain to me this, because it's a new thing. In fact, I was just talking with my son last night about this. Not less than 95% of the permanently installed luminaires used for plant growth and maintenance shall have a photon efficiency of not less than 1.6 micromoles per joule, as defined in accordance with ANSI ASABE S640. What is a photon and what is micromole per joule? No scientists in here that want to. Apparently, from what I could see, is this is not visible, but it stimulates. It's something that we can't see that's great for plant growth. And why do we think this is in the code now? And it's not strictly because they're growing lettuce and carrots and stuff like inside, is it? Actually, my brother has a place up kind of by Lake Tahoe, and they built a great big building up there to grow marijuana. And he said they've already closed the building because they spent so much money on the building, and the demand hasn't matched what they were hoping it would be. There's been a lot of competition, I guess. But anyway, I don't know if you've noticed, but there's a lot of places in big cities and stuff that they're taking vacant buildings and they're growing their lettuce and stuff like that for their use in the towns, and they're able to grow it perfectly and harvest it easily at just exactly the right time, and very efficient on water usage and everything else. So I don't think that's the end of that. We're going to see more and more of that. We already talked about tenant spaces. They get 5 credits. They don't have to comply if the entire building used credits 5, 8, and 9, and I can't remember what those are. But anyway, there's certain ones that if the building already has certain features, you don't have to. And previous occupied tenant spaces that complied with this code per C501. What's C501? Chapter 5 is existing buildings. And so you just need to look for all your exceptions on that. Last couple things. Escalators or moving walkways. Apparently these use a lot of power. You have a lot of mass that you're moving without people on it. And they literally, when they're at low usage times, and I've even noticed this out at the airport, when it's low usage, that the moving walkway slows down. And I've walked up to it, and as you get close, it speeds back up for you. And escalator energy recovery. This has been in the code at least 3 years, and I think it's been in the code 6 years, if I recall correctly. Escalators are supposed to have energy recovery on them. And what that means, has anybody driven an electric car? Do you have regenerative brakes? So what do the regenerative brakes do? Give them you're comfortable talking about it, aren't you?
Sure.
What's regenerative brakes?
Regenerative brakes capture the energy associated with slowing the car down and turn it to electricity to recharge the battery.
Exactly. My boy in California, you drive his car, his electric car, and you just about put your face on the steering wheel because he set his for maximum regenerative brake. So what he does is and it's completely different driving experience because You always have your foot on the gas, and as you're wanting to slow down, you just start backing your foot off. If you take your foot right off, it's like you put on the brakes hard. And his wife won't even drive his because, you know, that. And she has her set so that it's more normal feeling, you know. If you back off, and you're just coasting, yeah, it does give you a little bit regeneration, but you're capturing that energy. You know, it takes, you ever notice if you have a MPG indicator on your car, and your car gets 25 miles a gallon, when you take off from the intersection, what's your instantaneous miles per gallon? 5, 3, 2, 1. We're having to accelerate that mass. Well, that's a lot of energy that put into getting it up to speed. There's a lot of energy that we have to dissipate to bring it back down to zero. And where does that energy go? It goes into heat out of your brakes. And so with regenerative, we recapture that energy. Escalators apparently use a lot of power. And you might have even seen videos of when something breaks and it's shooting down because when it's full of people, because it literally has to break when it's loaded with people coming down. And so the code for several code cycles, and I'm sure that I could have missed it and others in here have missed it, when an escalator is installed, we should have been checking that they have regenerative brakes. And
A state elevator inspector look at that? Escalators and elevators, state?
the question is, doesn't the state inspector, escalator, elevator inspector look at it? He does, but do you think he's looking at the energy code?
No, but it's nice pants.
Who's in charge of looking at the energy code?
None of us.
We've been having discussions on this, haven't we, Jacqueline? Who's responsible for enforcement of the code? The building inspector's who's responsible. Who's responsible to build in accordance with the adopted code? The contractor. It's right in there, you know. And if either one doesn't do that, they're guilty of unprofessional conduct. So we really, and in fact, we're going to send out a letter because some choose not to do anything, and we're trying to get everybody on board nicely. But we have a responsibility. If you hold an inspector's license, a condition of your license is that you enforce the code to the best of your ability, and the same thing if you're a contractor. I've seen contractors in court before say, well, it passed inspection. Doesn't say anywhere in the state statute that you only have to build the code if the inspector catches it. It says you'll build according to the code. And so we all have a responsibility there. And I'm not beating you guys up because, hey, I've been out there. I know exactly what it's like. But we do need to try to do our best. And we have not been doing across the state as good a job as we could, and we definitely can do better, and that's going to be a lot of our focus over the next year or two. That's what we're hoping it can be, and I spend more time on that, kind of adjust where my time's spent, so we can do that. This isn't a big deal, but all the escalator people know about it, and there's even, as I read about this as I was studying for this, the escalator that's going up, there is so much mass in that movement up. When that person gets off or whatever like that, you can actually regen some of that energy, that you don't need as you slow it down because no one's on it. And so it works for both up and down. This one's everybody's favorite. Not everybody, but most people did not like ASHRAE because ASHRAE has had this requirement in the code already. And it is now in the IECC, and there's exceptions and such, but in the typical office space, they need to have automatic receptacle controls complying with that whole section, and it's basically half of the 15 and 20 amp receptacles installed in all these spaces need to be able to be automatically shut off. And at least 25% of those installed in modular furniture, cubicles and such, need to be able to be shut off. And then the code talks about all the options and the exceptions. The purpose is, just like the people that leave the lights on when they leave their office, there's a lot of stuff in your office that doesn't need to be on all night. And so when the building goes unoccupied, monitors shut off, coffee pots shut off, all this stuff. Things that have to stay on 24 hours can go in the receptacles that are not. The other half or whatever that is not, and so you just need to plug it into the right spot. And it's not a bad thing, it's a good thing. You can shut down a lot of stuff, especially those that have their little electric space heaters, whatever, underneath, you know. But you need to see the code on that. And another less popular, and this is the last one, energy monitoring. And some consider this overreach, but new buildings greater than 25,000 feet need to be equipped with to measure, monitor, and record and report energy consumption. The exception is R2s less than 5,000 feet, individual spaces with its own utility service. So most R2s have their own utility service already, so it doesn't matter. You can have a 500 unit apartment building and each one has their own meter, so they don't have to have that. But what energy needs to be monitored, and this was in ASHRAE for the last 3 years, individually, your total HVAC, your interior power, your interior lighting, your exterior lighting, plug loads, process loads, building operation, and miscellaneous loads. And so this is broken down in those specific areas. And why would we want to monitor those separately? So you can identify when something changes in one of them. This isn't because we're going to report it to Uncle Sam or something like that. It's for the building owners and building managers so that they know what's going on within their building. And with the control systems now, this is part of what I was talking about before. We have the ability to identify, all of a sudden there's something happening with my HVAC system. Maybe I got a chiller that's going bad. Maybe we have an issue with some lighting, or we have an issue with some lighting outside, or we have a high plug load. And, you know, so there's just a number of things that allow you to be able to be more proactive to when a problem occurs. We don't have to wait for a month or two and then finally go, I wonder why this bill is so high. It shows up really quick. And how's that? Exactly 3 o'clock. Please send your brilliant ideas or suggestions to me. If you need to contact me, I would appreciate a text or an email first if you can, simply because I have, boy, you're just in time, Jason. I'm more than happy to hear from you, more than happy to help you out. If you just give me a heads up first, and if you have a question, feel free to put it in an email, what your question is, so I can be more prepared to answer your question when I call you back or whatever the case. And with that, thanks so much. Again, I appreciate your input and you being here, and we'll see you next time.
Next time being April 6th, which would be a brunch and learn, where we're gonna do a breakfast half day for residential, quick guide and checklist.
Very good. Oh, and I didn't mention that. Thank you for saying that. One quick comment. I am going to be working on, many of you have seen my little residential quick guide that kind of goes through residential requirements. I'm going to try to create a block of time that for like this code, that I can put together a sheet that talks about lighting controls, or put a sheet together that that focuses on each one of these things, because there's just a lot there, and if I could give you a little bit of guidance on it, I think that it'd be a lot easier. And I'm updating on the residential side, and I know code officials don't like checklists, but I think I'm going to create some checklists for that jurisdiction that isn't doing anything yet, or that jurisdiction that's doing a little bit, just to help you walk through, and it'll help you train new guys and everything else. So thank you.
Thanks, Brent.